I just want to throw an open panel on here for you guys.
And you'd be squeezed as thin as a
Here
noodle.
y'all go.
You'll be extruded through the fabric of space and time, like toothpaste through a tube.
Today, we know more about black holes than ever before. But the more we learn, the more mysterious they become.
They're the most exotic objects in the universe. We don't have the physics to describe them.
No matter how well you understand them, they remain unreachable in some sense.
Gravity's at maximum. Man is about to enter the black hole.
So black holes have a pretty fierce reputation. And if you want a villain for a sci-fi movie, cast a black hole. But in reality,
Whoever's in here, what up, world? I'm going back to bed.
and where do they come from?
Tell them to show the channel love tonight. Y'all have some fun, enjoy. Open channel, open open chat. I'm going back to bed. I'll be in another room away from my phone. It's on charge live all night. Good night. Love y'all.
Nothing except gravity. Gravity at its most intense and overwhelming. So if black holes are all about gravity,
Gravity at its most extreme, what exactly is gravity?
we're all familiar with gravity.
Yep, it's Friday.
It rules our lives. But even so, for a very long time, how gravity actually works was one of the greatest mysteries. Over 300 years ago, Isaac Newton was fascinated with the behavior of moving objects. Eventually, he figured out his laws of motion. They work so well, we still use them today. But Newton's laws can only describe gravity's effects, not explain what it is. And here's where Albert Einstein comes in. Like Newton, he thinks about objects in motion. And he wonders what gravity actually is. Is it a force, or could it be something else? Here's what concerns Einstein. Take this apple. I can't move it without touching it. But if I drop the apple, it moves toward the earth. But what if I take my hand away? And the floor, and the basement, and the floor below that? Then what happens? The apple just keeps falling. Einstein realized that gravity had something to do with falling. Now, if I throw the apple, it falls along a curved path. But imagine I could get the apple moving much faster. Eventually, if I get the apple moving really, really fast, say 17,000 miles an hour, its curved path matches the curve of the Earth. The apple is in orbit, falling freely, just like the International Space Station and the astronauts inside it. According to Einstein, the apple and the space station and the astronauts are all falling freely along a curved path in space. And what makes that path curved? The mass of the Earth.
Einstein came up with a supremely simple concept, and that is that space and time is bent by the Earth and by the sun and by all the objects in the world.
So according to Einstein, the mass of every object causes the space around it to curve.
And that was Einstein's conception. There are no forces anymore. There's just objects bending space-time and other objects following the straightest line through it.
All objects in motion follow the curves in space. So how does the Earth move the apple without touching it? The Earth curves space, and the apple falls freely along those curves.
That, according to Einstein's general theory of relativity, is gravity, curved space. And that understanding of gravity, that an object causes the space around it to curve, leads directly to black holes. But it's not Albert Einstein who first makes the connection between gravity and black holes. It's another scientist.
Karl Schwarzschild was a German astronomer, head of the Potsdam Observatory in Germany.
Ever since he was a teenager, he had been calculating complicated features of planetary orbits.
As Einstein unveils his theory of gravity in 1915, Karl Schwarzschild is in the German army, calculating artillery trajectories in World War I.
And just weeks after Einstein presented his papers, Schwarzschild, then on the Russian front, quickly got a copy and was mapping the gravitational field around a star.
Einstein had gotten at it through a series of approximations, but Schwarzschild, sitting on the front with bullets and bombs flying, calculated an exact solution to Einstein's theory and sent it to Einstein. Einstein was astonished. He hadn't even imagined that you could solve these equations exactly.
But Schwarzschild isn't done. In his solution to Einstein's equations, he discovers something Einstein himself had not anticipated.
Schwarzschild said, I can calculate this strange distance from a gravitating object that represents a kind of boundary.
Schwarzschild mathematically concentrates a mass, for example, a star, into a single point. Then he calculates how that mass would bend space and curve rays of light passing nearby.
As he, through his mathematics, aimed particles of light or matter towards this point, there was this boundary surrounding the point at which the particles would just stop. The particles disappeared. Time stopped.
Schwarzschild has discovered that a concentration of mass will warp space to such an extreme that it creates a region of no return. Anything that enters that region will be trapped, unable to escape, even light.
It's like those roach motels. You can check in, but you can't check out. Once you go across that boundary, even if you can sail through, there's nothing you can do to get out. There's nothing you can do to signal out. It becomes this strange cut-off portion of space-time.
What Karl Schwarzschild has discovered is that any mass compressed into a small enough space creates what we today call a black hole. But Albert Einstein, whose own theory of gravity predicts such a thing, cannot believe it can happen in the real world.
Einstein didn't think that nature would act like this.
He didn't like this idea.
Karl Schwarzschild becomes ill and dies before he has a chance to further investigate his own discovery. 2.5 years later, in November 1918, World War I ends. The strange theoretical sphere discovered by Karl Schwarzschild seems destined to be forgotten. Nothing but a curious historical footnote. But in the coming decades, physicists learn more about the atom and about how fusing atoms powers stars, a process called nuclear fusion. Some begin to wonder if something like a black hole could actually come from a star. But not just any star. It would have to be big.
Stars are born in litters, and you get a distribution of sizes and masses. Thousands of little stars. And a few big stars, very big stars, incredibly massive.
Stars are in many ways similar to living creatures. Like humans, they have life cycles.
Investigating stars' life cycles in the 1930s, two visionaries, Subramanian Chandrasekhar and Robert Oppenheimer, discover that the most massive stars end their lives very differently from smaller ones.
The life cycle of a star really depends on its mass. The mass of a star determines what's going to happen after it finishes burning its hydrogen fuel.
All stars start out burning hydrogen, the lightest atom, using hydrogen atoms into helium, working their way up to heavier elements. Gravity wants to crush the entire mass of the star, but the enormous energy released by fusion pushes outward, preventing the star from collapsing.
Stars are stable because we have an outward moving pressure due to nuclear fusion, and that's balancing with the inward force of gravity.
Smaller stars can't fuse elements heavier than helium. But in the most massive stars, fusion crushes heavier and heavier atoms, all the way up to iron.
Iron is such a massive element, it has so many protons in it, that by the time you fuse iron, you don't get any energy back out.
Iron is a dead end for stars. Fusing atoms larger than iron doesn't release enough energy to support the star. And without enough energy from fusion keeping the star inflated, there's nothing to fight gravity.
And gravity wins. And so the entire star collapses.
Very rapidly, trillions of tons of material come crashing down, hit the dense core, and bounce back out, blowing off the outer layers of the star in a massive explosion. A supernova. The more mass, the more gravity. So if the remaining core is massive enough, gravity becomes unstoppable.
There's no known force to prevent the collapse to an infinitesimally small dot.
Gravity crushes the stellar core down smaller and smaller and smaller until all its mass is compressed in an infinitely small point. A black hole. The theory makes sense, but most physicists remain skeptical about black holes.
Einstein and Eddington and all the sort of, preeminent astrophysicists in the 1930s to 1950s did not believe that they were actually real. It remained a solution, a mathematical enigma for a very long time. So it took a long time for people to even start looking for them.
It's not until the 1960s that the idea of a supernova creating a black hole is taken seriously. Princeton physicist John Wheeler, who had originally been a skeptic, begins to use a name from history for these invisible objects. Black hole.
The term black hole actually originates in India. The black hole was the name of an infamous prison in Calcutta.
Still, no one has ever detected any sign of a black hole. Then in 1967, graduate student Jocelyn Bell discovers a strange, extremely tiny, dead star that gives off very little light. A neutron star. The cold remains of a stellar collapse. The neutron star gives astronomers more confidence that black holes, much heavier dead stars, might also exist. A half century after Karl Schwarzschild mathematically showed that black holes are theoretically possible, scientists have identified a natural process that might create them: the death of large stars.
So these giant supernova explosions of extremely massive stars make black holes.
Any star that is born with a mass that's about 10 times the mass of the sun or higher will end in a black hole. So our galaxy is replete with little black holes, which are the stellar corpses of generations of stars that have come and gone.
So what are these invisible stellar corpses like? Imagine I'm exploring space with some advanced technology for interstellar travel so that we could visit a black hole, maybe one in our own galactic neighborhood. This particular black hole isn't very big, only about 10 solar masses, meaning 10 times the mass of the sun. And like all black holes, it has an event horizon. A distinct edge to the darkness. That's the boundary Carl Schwarzschild first discovered, where gravity is so strong that nothing can escape, not even light. And that's where we're going. As we get closer, some very strange things begin to happen. Look at the edge of the black hole. See how the image of distant stars is distorted and smeared into a circle? That's gravitational lensing. The black hole's extreme gravity bends the path of light passing by, so that a single point of light, like a star, briefly appears as a ring around the event horizon. I'm now deep in the black hole's gravity well, and we're going to start experiencing the effects. The extreme gravity actually slows down time relative to the Earth. From their point of view, I appear to be slowing down. But from my point of view, time on Earth is speeding up. Now let's say I want to get even closer by taking a spacewalk. The way the black hole slows down time is about to get even more pronounced.
To keep track of the changes I'm about to experience, I'm turning on this strobe light. It'll blink once a second. From here, I can see the shadow of the event horizon approaching, and my light blinking normally. But watching from the ship, the closer I move toward the black hole, the more slowly I appear to move. The pulses are nearly infinitely spaced. So it looks as though I'm frozen in time. For me, everything is completely normal, even when I reach the event horizon. If you waited long enough, maybe millions or billions of years, the ship would finally see me disappear. And that's the last you'd see of me. What's inside a black hole? That's still a mystery. And even if I find out, I can never go back and tell you. But I can say this. Black holes may be dark from the outside, but inside they can be bright. I can watch the light from the galaxy that's fallen in behind me. And that's the last thing I'll ever see. Unfortunately, the fun is about to end. Now that I've crossed the event horizon, I'm falling toward the center, where all of the mass of the black hole is concentrated. And I'm beginning to get stretched. As I fall in, the gravitational pull at my feet is stronger than at my head, and my body is starting to get pulled apart. I'll be stretched as long and thin as a noodle, spaghettified, and ultimately I'll end up completely disintegrating into my fundamental particles, which are then crushed to an infinitely small point.
A singularity, where everything we understand about space and time breaks down. Or maybe the black hole, less than 40 miles across on the outside, is as big as a universe on the inside. And as I pass through, my particles will join the primordial soup of a new beginning. So that's what theory tells us we might experience if we could travel to a black hole. But how can we know for sure? How do you investigate something you can't even see?
There are ways to investigate if something is happening somewhere, even if I can't see that thing directly. Take Yankee Stadium. What's happening inside there? Is there a game going on? I can't see the field. I can't see any players or baseballs or bats, but I can definitely tell if there's activity around the park.
It's pretty clear something is going on. It might seem obvious, but whatever it is, I can learn a lot just by observing the happenings around the stadium.
And these do look a lot like baseball fans. And that's the way we investigate black holes, by observing the effect they have on their surroundings.
But what sort of effects? How might a black hole reveal itself? Starting just before World War II, two monumental discoveries are about to radically change astronomy. In 1931, Bell Labs engineer Carl Jansky picks up mysterious radio waves emanating from deep space. Then the sky gets even stranger. When scientists mount Geiger counters on captured German rockets and discover the cosmos is also full of X-rays. These discoveries give astronomers important new tools that will revolutionize the hunt for black holes and dramatically expand our vision.
What our eyes can perceive is a very narrow part of the electromagnetic spectrum.
If the electromagnetic spectrum were laid out along the Brooklyn Bridge, the portion we can see with our eyes would be just a few feet wide. Electromagnetic radiation includes waves of many different frequencies: radio waves, microwaves, infrared and ultraviolet light, X-rays, and gamma rays. Radio and X-ray astronomy open up the sky, revealing dim or even invisible objects, blasting out powerful energy no one knew was there.
They began to realize that this very placid thing that we see out there, all this very quiet thing that looks like nothing is happening and the only thing that's moving is the planets, found out that there was madness going out there. There was chaos out there.
X-rays come from the high energy end of the spectrum. What is creating all this energy? This much is certain. Whatever the source, it is invisible to ordinary telescopes, and it is hot.
X-rays come from things which are at temperatures of millions of degrees, even tens of millions.
One of the first of these X-ray sources to catch the attention of astronomers is named Cygnus X1.
Cygnus, it was in the constellation Cygnus. X, it was an X-ray source. 1, it was the first one he found.
In 1970, Paul Murden is a young English astronomer trying to secure his next job.
I was a research fellow. I was coming to the end of my 3-year contract, and I thought, what can I contribute to finding out what these things are?
Murden works in a 15th century castle surrounded by telescopes, the Royal Observatory. Using the largest telescope in England, he begins searching the area of the constellation Cygnus, the Swan. He decides to hunt for pairs of stars. Pairs of stars are called binaries, They may sound exotic, but they're not at all uncommon. Many of the stars we see, perhaps half, are actually binaries, pairs of orbiting stars locked together by gravity. But Murden wonders, is it possible there are binaries where only one of the stars is visible?
I thought that maybe there was a kind of a star system in which there was a star, one ordinary star that made light, and then there was another star nearby that made X-rays.
The telltale sign of a binary is that the stars are moving around each other. So Murden begins searching for a visible star that shows signs of motion.
Sometimes it's coming towards you, sometimes it's coming away, sometimes it's coming towards you, sometimes it's coming away.
When the star is moving toward us, it appears more blue as the wavelength of its light gets shorter. Moving away, it appears more red as the wavelength of its light gets longer. This is known as Doppler shift. After looking for color changes in hundreds of stars in the area of Cygnus, Murden spots a possible suspect, a visible star whose light is shifting as though moving around.
It very clearly was a binary star, a double star. The star was moving around and around with a period going around once every 5.6 days.
But whatever it's going around can't be seen.
There was no trace in the spectrum of the second star. There was one star there, there wasn't the second star there.
Murden has a binary pair in which only one star is visible. The second object emits X-rays, has enough mass and gravity to dramatically move a star, but gives off no light. Could it be the corpse of a star massive enough to become a black hole?
The crucial issue in deciding whether Cygnus X1 was a black hole was to measure the mass of the X-ray emitting object.
It would have to be very massive, at least 3 times the mass of our sun. If not, it's probably just a neutron star. A collapsed star that's dense, but not heavy enough to be a black hole.
So the observers needed to come up with a conclusion that the dark object, the X-ray emitting object in Cygnus X1 was heavier, hopefully substantially heavier than 3 solar masses.
From his observations, Murden is able to make an estimate of the mass of the invisible partner.
And the answer came out to be 6 times the mass of the sun. So there was a story then that Cygnus X1 was a black hole. And the key to the argument was that the mass of the star you couldn't see was more than 3 solar masses. When I'd finished writing it all out, I sat back and thought, it's a black hole.
This would be the first actual detection of a black hole. It's a huge claim, and Murden will have to convince skeptics, starting with his boss.
The Astronomer Royal, Sir Richard Woolley, he didn't really go for black holes. It's all fanciful. It's kind of, a lot of people in California were talking about this. There are a lot of funny people in California, you know, a lot of hippie type people.
People like theorist Kip Thorne.
So I was nervous about it. I was nervous about the scale of the discovery, and actually so were other people all around me. I was working with a fellow scientist, Louise Webster, and we were modest about the claim that we were making because we knew what people would think of it. And if you look at the paper we published, it just mentions the word black hole once, right at the end. We think this might be a black hole.
The Paul Murden Louise Webster paper appears in September 1971. Other astronomers agree it could be a black hole, but no one knows for sure. 3 years later, Kip Thorne and the noted British physicist Stephen Hawking make a now famous wager about Cygnus X1.
We made a bet as to whether Cygnus X1 really was a black hole or not.
The bet is partly in jest. Both men hope it is a black hole. But Hawking, not wanting to jinx it, bets against his own wishes.
Stephen claims that Cygnus X1 is not a black hole, and I claim it is a black hole. And so we signed that bet in December 1974. And gradually, the case that it really was a black hole became stronger and stronger and stronger. So in June of 1990, Stephen broke into my office and he thumbprinted off on this bet, conceded the bet in my absence. I came back from Russia and discovered that he had conceded.
Now, by 1990, the evidence of Cygnus X1's mass may be strong enough to settle a bet between two friends. But the original estimate wasn't precise enough to be definitive. In order to calculate mass, Paul Murden had to rely on rough estimates of the distance to Cygnus X1, which varied by a factor of 10. And the question wouldn't be answered for another 20 years, until astronomer Mark Reed became intrigued by the puzzle. Reed is an astronomer at the Harvard-Smithsonian Center for Astrophysics when he sets out to conclusively prove that Cygnus X1 is a black hole by measuring its precise mass. But how can you measure the mass of an invisible object? Using laws developed by German astronomer Johannes Kepler in the 1600s, it's possible to calculate the mass of a celestial object, but only if you know its distance.
Distance in astronomy is absolutely fundamental. If you don't know distance, you don't know what the object is. It could be a very nearby firefly-like thing. It could be a very distant, huge star, much, much bigger than the sun.
So to get the true, precise mass of Cygnus X1 and confirm that it is a black hole, Reed needs to know how far away it is. But how can he measure the distance to a star? The secret lies in a familiar phenomenon, parallax. It's what our eyes and brains use to see in 3 dimensions.
You can put your finger up at arm's length, look at it, and close one eye. I'm closing my left eye, and I'm looking at my finger relative to the wall in the background there. And now if I open my eye, close my right eye, I see my finger has appeared to move with respect to the original position. And that's because our eyes are separated and we view from different vantage points.
To use parallax to measure distance to an object in the sky, astronomers let the motion of the Earth provide the 2 different vantage points.
Imagine Cygnus X1 is right here, and the Earth and the Sun are over there. Now, the Earth goes around the Sun once a year. And in the springtime, the Earth ends up on one side of the Sun, and we observe Cygnus X1 along a ray path like this. And 6 months later, the Earth goes around the Sun to the other side. We get a different vantage point from Cygnus X1.
Now he has a triangle that goes between the Earth at its 2 positions and Cygnus X1. We know the base of the triangle, the diameter of Earth's orbit. And the principles of geometry tell us that all we need to calculate the distance is the size of the angle at the top.
And we measure this very small angle here at the point at Cygnus X1. And then from direct geometry, we can calculate the distance to Cygnus X1, and from that infer a very accurate mass.
The concept is simple, but Cygnus X1 is so far away that the angle to be measured is minuscule, a tiny fraction of 1 degree. It's smaller than the angle span by Abraham Lincoln's nose on a penny in San Francisco, viewed from New York. Because the angle is so very tiny, it can't be measured by any one telescope. But Reed's team has a solution.
We take 10 radio telescopes that are spread across the continental US and to Hawaii, and to St. Croix in the Virgin Islands. We use these telescopes simultaneously, and we synthesize in the computer a telescope that has the diameter of the size of the Earth. That gives you incredible angular resolution.
Using this technique, Reed's team determines that Cygnus X1 is 6,000 light years away.
With the new distance we got, the 6,000 light year distance, we were able to determine that the mass is about 15 solar masses, easily a black hole.
40 years after it was identified as a possibility, Cygnus X1 is now widely accepted as the first confirmed black hole.
It's an understated paper, and the fact that my name was on it and Louise Webster's was on it did us a lot of good in our careers. I think as a result of this discovery, I got offered a permanent job, and it was a great celebration for the family. So it worked out very well for me, as well as getting the intellectual satisfaction of solving a problem.
So finally, after years of speculation, we have a real black hole. Not only that, but a black hole that's blasting out X-rays and has a companion star. If we could visit in my imaginary spaceship, what would we see? The distance to Cygnus X1 has been established at 6,000 light years from Earth. And its mass is 15 solar masses, or 15 times the mass of the Sun. And Cygnus X1 is surrounded by an accretion disk, a disk-shaped cloud of gas and dust outside its event horizon, the point of no return. As gravity pulls matter toward the black hole, the cloud starts rotating, just like water being pulled down a drain. Within that accretion disk, particles closest to the black hole whip around at half the speed of light. It's like a giant particle accelerator in space. But why does it emit X-rays? As those particles race around, they collide, which heats them up to millions of degrees. When they get that hot, particles blast out X-rays. And it's those X-rays that first led astronomer Paul Merton to investigate this black hole nearly 5 decades ago. And there's something else about Cygnus that's different. It has a companion star. This blue supergiant star orbits the black hole once every 5.6 days. It orbits so close to Cygnus X1 that the black hole strips material off the star and pulls it into the accretion disk. Some of that material will cross the event horizon and get swallowed up, but not all of it.
Some of the stuff actually comes back out before ever entering the black hole. Kind of like a toddler eating. Half the pasta ends up on the floor, half of it maybe on the ceiling, and some of it in the mouth.
One of the most striking and enigmatic features of Cygnus X1 is its enormous jets. These beams of particles and radiation stream outward from Cygnus's north and south poles, perpendicular to the accretion disk. There's still a lot we don't know about these jets, but they are tightly focused and extremely powerful, blasting out at nearly the speed of light and extending well beyond Cygnus.
When gas gets to these high temperatures and produces the light, there's also a little bit of a magnetic field that forms around them. And we don't understand exactly how, but these magnetic fields help collimate these massive outflows from black holes. Powerful hoses, if you will, that just spew matter out.
So that's Cygnus X1, if we could see it up close. A growing, feeding black hole with huge jets, blasting particles way out into the universe.
They're almost these breathing, fire-eating demons, if you will. They flicker, have bursts. It's a very violent fireball, very active.
What was once a bizarre mathematical curiosity has now become quite real. After decades of skepticism, scientists now accept that burned out corpses of large stars can trap light inside them, warp space and time around them, attract matter, and accelerate it to mind-boggling speeds.
Black holes seem like such a radical idea that we shouldn't accept it. But bit by bit, the evidence for black holes has gotten stronger and stronger. And we've seen these amazing things.
At least 20 black holes have been found in our galaxy. X-ray binaries like Cygnus X1. And there are probably millions more of these massive stellar corpses in our galaxy alone. Still, a stunning surprise awaits. Everything astronomers think they know about black holes, and much of what they believe about the universe itself, will be upended by a shocking discovery. The revelations begin when radio telescope surveys of the sky detect mysterious hot spots emitting radio energy.
They were coming from what looked like stars.
Because these objects resemble stars, but were discovered through radio signals, astronomers name them quasi-stellar radio sources, quasars. But are they stars or not? The first step in investigating them is to figure out what they're made of. To do that, astronomers analyze the electromagnetic energy they emit. Every element has a unique spectral fingerprint. For example, carbon, helium, hydrogen. These lines reveal the chemical makeup of a star. But the spectrum of a quasar turns out to be incomprehensible.
They looked at it and it was gibberish. It didn't look like there were any emissions from elements that they knew.
What are they missing? There has to be a clue somewhere. Finally, in 1963, Caltech astronomer Martin Schmidt finds it, hiding in plain sight. Buried in the quasar spectrum is the fingerprint of hydrogen.
He noticed something familiar, but it was in the wrong place. The fingerprints of hydrogen had been shifted way off to the red.
It was hard to spot because the spectral lines of hydrogen were radically shifted toward the lower frequency end of the spectrum. And that could only mean one thing. The quasar is moving away from us at fantastic speed. But astronomers have almost never before seen light shifted to such an extreme. Like a familiar sound shifting too low to understand. The light from quasars has shifted to such a degree that hydrogen is unrecognizable. This extreme amount of shift means quasars are racing away from us at blinding speeds. The reason? It's the legacy of an event that occurred almost 14 billion years ago, the Big Bang. The beginning of our universe. And ever since, the universe has been expanding, carrying with it all the objects it contains, including quasars.
Almost no one had ever seen anything moving away at that high speed. This made this object almost the furthest away thing that had ever been seen, which meant the thing itself had to be so luminous, and you had to account for that.
2 billion light years away, putting out the energy of 1 trillion suns each second. What could possibly create that?
No one had any idea what could be powering these things. Where could all of this energy come from?
If you work out through calculations, it can't be chemical energy. they knew it couldn't be nuclear energy.
There's no way a quasar could be a star. No amount of nuclear fusion could produce that much star power.
The only engine that could possibly put out that much energy is gravity.
Gravity. In everyday life, we can overcome gravity easily. But when concentrated to an extreme by a black hole, gravity is overwhelmingly powerful. A handful of scientists start wondering, could quasars perhaps be powered by gravity engines? What if the energy blasting out from quasars is coming from bright accretion disks around black holes?
To produce that kind of energy, that kind of brightness, it has to involve a black hole.
But not just any black hole.
Whatever was the source of the emission from a quasar had to be massive. How massive? Well, millions or billions of times heavier than the sun.
Millions or billions of times heavier than the sun. Cygnus X1 is only 15 times the mass of the sun. The black holes powering quasars are an entirely different category of black hole. Supermassives. And they seem to be located in the centers of galaxies. But what about our own galaxy? Could there be any supermassive black holes closer to home? The center, where any supermassive would be found, lies in the direction of the constellation Sagittarius, the Archer. Now, Sagittarius isn't just any constellation. It's in the direction of the center of our own Milky Way galaxy. But since we live inside the Milky Way, we can't see the galaxy the way a space traveler would. But I can use my trusted imaginary star machine to show us the galaxy from the outside. Our home is a spiral galaxy, hundreds of billions of stars drawn together into a gigantic disk. It's wide, about 100,000 light years across, but it's relatively thin, only about 1,000 light years thick. And the whole spiral slowly rotates. Our solar system is here. And here, 26,000 light years from the Earth, is the center, which we see in the direction of Sagittarius. In this dense center, there are millions of stars and lots of dust and gas. So that's the view of our galaxy from the outside, thanks to my imaginary technology. But since we live inside the Milky Way, when we look towards the center, we're looking through much of our own galaxy, which means it appears to us as a band of stars and dust across the sky, a Milky Way. Deep inside this band of stars and dust, could a supermassive black hole be lurking?
The data that we're getting now.
In the 1990s, astronomers grow determined to solve the mystery, to peer through the murky Milky Way and learn what, if anything, is at its center. One of them is Andrea Ghez.
1 in 20.
Ghez takes on a daunting challenge. She will try to track individual stars orbiting the center of the galaxy.
The essence of this experiment comes from watching stars orbit the center of the galaxy. So you want to find the stars that are as close to the center of the galaxy as possible, which means that I want to get access to the largest telescope I can possibly get my hands on.
And that means coming here. The summit of Mauna Kea, a dormant volcano almost 14,000 feet above the beaches of Hawaii. High altitude and low humidity make this the ideal place for astronomy. The instrument Ghez uses is Mauna Kea's Keck Observatory, one of the largest in the world. But But despite its size, Keck has the same problem as all telescopes on Earth: atmospheric distortion.
Think about looking at a pebble at the bottom of a river. The river is moving very quickly, and your view of that pebble is distorted.
Like a river, the Earth's atmosphere is constantly changing, bending light like a funhouse mirror. To compensate for this, Keck pioneers the scientific use of a declassified military technology called adaptive optics. First, they shine a laser into the sky, creating an artificial guide star. The turbulent atmosphere distorts the guide star, but the computer knows what it should look like and adjusts the telescope mirror accordingly.
So if you look at yourself in a circus funhouse mirror, you look completely distorted. And the goal of the adaptive optics system is to introduce a second mirror that's the exact opposite shape and make you look flat again.
Buried deep inside the telescope, the deformable mirror changes shape up to 2,000 times a second to reverse the atmosphere's distortion.
And it has allowed us to take the sharpest images ever obtained of the center of the galaxy.
The sharpness of those images allows GES to make out individual stars near the center, a huge advance in astronomy. She begins recording their positions in 1995.
And every year since then, we've taken an image. Just take a picture.
Putting those annual snapshots together creates a time-lapse movie of stellar orbits. And what those movies reveal is astounding. The stars are whipping around the center of the Milky Way at phenomenal speeds.
These things are moving at several thousand, up to 10,000 kilometers per second, or 10 million miles per hour. They're really hauling.
To go that fast, the stars must be orbiting something extremely massive.
The mass that we infer is 4 million times the mass of the sun.
What could be 4 million times the mass of the sun, yet be completely invisible?
That is the proof of a black hole.
And not just any black hole, a supermassive, silent and sleeping, right in the center of our own galaxy.
In fact, this is the best evidence to date that we have for the existence of supermassive black holes, not only in the center of our own galaxy, but anywhere in the universe.
A supermassive black hole, 4 million times the mass of the sun, in the very center of our own Milky Way galaxy.
From a cosmic perspective, it's right next door. And it raises a profound question. There are billions of galaxies out there. If ours has a supermassive black hole at its center, and if quasars are found at the centers of their galaxies, what about the others?
Are there black holes at the centers of galaxies? If they are, how common are they? We simply didn't know.
Could astronomers ever hope to find what lurks at the centers of other galaxies, millions of light years away, as GES did in our Milky Way? It would take another innovation in astronomy to make that possible.
And liftoff from the Space Shuttle Discovery, on the universe.
When the Hubble Space Telescope starts delivering clear images of distant galaxies, a team of astronomers gets to work. They become known as the Nukers because their focus is galactic nuclei, the centers of galaxies. One of them is Todd Lauer.
Step one, we take a picture of a galaxy with the Hubble Space Telescope. It shows us where the stars in the galaxy are, tells us its structure and exquisite resolution.
The key to finding supermassive black holes is to learn how fast the stars in the galaxy are moving. Galaxies outside our own are much too far away to measure the speed of individual stars. But by analyzing the way light is shifted from blue to red at different points in the galaxy, astronomers can put together an average speed of stars orbiting the center. It's accurate enough to create a replica in a computer.
The second step, where the real work begins, is to try to model the observations. And we actually do that by building models of galaxies in the computer.
It's known as Schwarzschild's method, developed by Princeton astronomer Martin Schwarzschild, son of Carl Schwarzschild, whose mathematics first described the possibility of black holes.
Martin Schwarzschild's trick was he would actually build up a model of the galaxy that not only had where the mass was, but it also had how the stars were moving.
For each galaxy they investigate, the nukers painstakingly build a computer model, and then using trial and error, adjust the parameters of mass and velocity, trying to make the model match the original observations they got from the Hubble.
And we say, let's try a star here, let's try one over here, let's have it go around this way, let's have this one go around that way. And we do this thousands and thousands of times until we build up a library of how stars can orbit in this galaxy. Success is when observations of the model match the observations taken with the Hubble Space Telescope.
But that doesn't happen. The models are missing something.
We try it again and again and again, all with no black hole yet, and say, gee, we really can't get the observations explained by the model.
Only when they add an enormous invisible mass at the galaxy's center does the model match the Hubble observations.
Almost always, we have to put in a black hole at the center. We can't match the observations without a black hole in the model.
Of roughly 36 galaxies that the nukers investigate, virtually all of them require a supermassive black hole. And since then, other observations have made us even more certain that supermassives and galaxies go together.
Every galaxy we've looked for one, we have found a supermassive black hole in its center.
It's a stunning revelation. Supermassives, once an entirely unexpected category of black holes, may be common. Not only at the center of our galaxy, but of all galaxies. Take galaxy M31, also known as the Great Andromeda Galaxy. It's 2.5 million light years away. On a clear night, you can see it from Earth. But even with the Hubble Space Telescope, we can't make out precise details of its center. Still, we're pretty sure there's something extremely massive hiding there. What if we could take a closer look? What if we could visit a galaxy far, far away? As we enter the outer part of Andromeda, we're still too far away to see what's lurking at the center. But we can make out a dense cluster of stars in the core, and that could be a sign that there's a giant black hole nearby. Billions of years ago, it would have been surrounded by gas and stars and other small black holes. The black hole may have powered a quasar, feeding mad and blasting out blinding radiation. Over hundreds of millions of years, it would have consumed all the available gas and the closest stars. These days, it's relatively quiet, but it has some distinctive features we've never seen before. First, it's colossal. If it were dropped in our solar system, Mercury, Venus, Earth, and Mars would all be trapped inside the event horizon. That's big, but it's nothing compared to the sheer mass, 100 million times the mass of the Sun. And the destruction won't end there. Jupiter won't last long. The gravitational field of the supermassive will grab hold and swallow it whole. Eventually, Saturn will suffer the same fate. The outer planets might survive, but in cold and dark orbits. This black hole rotates rapidly, distorting and dragging the fabric of space-time. Like all black holes, the event horizon is completely featureless. Remember, there's nothing there. It's just a boundary that conceals the interior. But the accretion disk can tell us a lot about what's going on. That's the fiery ring of gas and dust around the black hole. Imagine if we could release a swarm of autonomous robots to explore the accretion disk. The disk is spinning at an incredible speed, as much as half the speed of light. If Jupiter moved that fast, it would complete its entire orbit in a few hours. The region around the black hole is a cosmic tornado. Now our swarm is caught in the whirlwind too. They're like tracers, dropped into the storm to map movement. The middle robot can send us images. It's following the leader like a race car speeding around the track. From here, the extreme warping of space-time around the black hole plays crazy tricks on our eyes. It looks like there's one accretion disk whipping around the equator and another arcing over and under the poles. But that's an illusion. The black hole's extreme gravity bends the path of light emitted behind the black hole and makes it look like the accretion disk is both above and below. There's actually nothing around the poles. It's just the passing light rays. That's gravitational lensing again. Drawing much closer to the event horizon, the gravitational lensing would become so extreme that one of my robots could look straight ahead and eventually see its own back, the light forever trapped in an eternal circle. So that's our tour of the supermassive black hole at the center of the Andromeda Galaxy. Pretty amazing. Also amazing, nothing in the mathematics led scientists to imagine that black holes could get that big. As strange as they are, ordinary stellar mass black holes were at least predicted by theory. Supermassives are a complete surprise.
For the stellar mass black holes, people thought about them from a theoretical perspective, and then we found them observationally. The supermassive black holes, the story has been inverted. We actually found evidence of them observationally first. And now we're working on the theory of how did these things come into being.
We already know that stars can collapse to create ordinary black holes, but supermassives are bigger by many orders of magnitude. Cygnus X1 is 15 times as big as our sun. The supermassive at the center of our Milky Way is 4 million times as big as our sun. The one in the Andromeda Galaxy is 100 million times as big as our sun. And it's not the biggest, not even close. There are supermassives 10, even 20 billion times the mass of our sun. How is it possible to make such gigantic black holes? Could supermassives have come from collapsed stars? That seems very unlikely. We don't know any stars billions of times bigger than the sun.
We know about black holes you might get from a dying star. They have several times the mass of the sun contained within them, but millions of times the mass of the sun. If that's the case, a dying star cannot have possibly made it.
So do these supermassives, millions or even billions of times heavier than the sun, somehow just grow, packing it on like voracious giants?
The wild thing about black holes is that they feed. They're constantly devouring anything that comes within their sphere of influence, so they grow.
But how exactly do they grow? What do they eat, and where do they find it?
We believe that black holes grow by accretion of gas. And the way this works is that you have a lot of gas around in the center of a galaxy, and this gas would then assemble and form an accretion disk.
The accretion disk is made up of hydrogen, helium, and other elements in a gaseous form. The immense gravity of the black hole pulls the gas in toward it. As it swirls around, it orbits closer and closer to the black hole, and the feeding begins.
The stuff in the inner regions would get slowly pulled in, sped up, will reach the event horizon, and then that's it.
Whatever gas crosses the event horizon disappears forever. The black hole has absorbed that material.
So it actually adds to the mass of the black hole.
So this is one way a black hole can grow, gradually nibbling gas and dust. But it's not the only way. Cygnus X1 has been slowly stripping material off a nearby star, a process that will likely go on for thousands or millions of years. But what if a black hole could rip an entire star apart in just a matter of years or even weeks? That would be a very violent event, and a team of space explorers is on the lookout. This is the Operations Control Center for a space telescope.
Ivy 5x5, how many? We show beginning of track at 0330.
The Chandra X-ray Observatory.
Copy, Roger, lead 16 minutes, 1-6.
Orbiting up to 86,000 miles above the Earth, Chandra takes high-resolution images of objects that emit X-rays. This is one. A short-lived, extremely violent event called a transient, which fascinates James Guillochon.
Supernovae, the destruction of planets by their host stars. I'm just fascinated with destroying things for science.
James is investigating a mystery discovered by a colleague, Dasheng Lin. This blur on James's screen is actually a massive sudden burst of X-ray energy, caught by accident.
This little smudge popped up in the background in this image, and given its great distance, it's actually tremendously bright.
Could it be a black hole caught in the act of being born in the violent collapse of a huge star? A supernova. Perhaps. But the intense radiation released by supernova would only linger for a few months. So how long has this mystery object been blasting out X-rays? To find out, they look at images of that same part of the sky taken at earlier dates. 2015, 2011, 2008, 2005 July, 2005 April. No X-rays detected. But the X-rays are there just 3 months later in July. And the powerful, bright signal has continued for more than 10 years, from July 2005 to the present, far too long to be a supernova. So what could it be? A black hole that's not feeding is quiet and completely dark. It won't show up on any telescope. But a black hole that is feeding is different. When it feeds, it blasts out X-rays. So could this be a black hole that's suddenly begun devouring something big?
What effect will this have on anything that comes near? What would it do to a star that wanders too close? Well, it will flay a star, layer by layer, ultimately devouring the entire star.
Unlike Cygnus X1, this is no mere nibbling. This is a 10-year feeding frenzy. A massive black hole devouring an entire star in a cosmic blink of an eye. It's the result of a chance collision, when an unlucky star wanders too close and the black hole's extreme gravity actually rips it apart.
The gravity from the black hole will progressively get stronger and stronger as the star gets near. And at that point, the star will begin to deform.
It's called tidal disruption. It's similar to the way our moon's gravity easily moves all the world's oceans. The tides caused by a black hole would be billions of times stronger and much more violent.
You have these events where a star could be ripped apart by the black hole, so you would see sort of a plume of light from the last gasp of the material in the star.
But there is a chance for some part of the star to escape, as James illustrates.
As the star is elongated by the black hole's tidal forces, it will essentially be feeding the black hole at the same time as half of it is trying to escape. So everything above this point approximately will have the chance of leaving the galaxy. It's moving that rapidly. And everything below this point will fall back onto the black hole and eventually be consumed by it.
So this is another way for a black hole to gain weight. Unlike the slow, steady nibbling of Cygnus X1, this black hole is devouring most of an entire star in one gulp. But whether a black hole feeds suddenly by swallowing half a star or steadily through accretion, astronomers still face a problem when they try to understand how supermassives got so big. The timing problem. The trouble begins with the very oldest supermassives, quasars. Those very bright, very distant, and ancient objects first discovered in the early 1960s.
The conundrum was when we started finding these quasars, very bright quasars, very early on in the universe.
They're giving off so much energy that they have to have very massive, supermassive black holes at their center.
But quasars are extremely far away, which means that they're part of the very early universe, which began nearly 14 billion years ago.
Bright quasars, 600 million years after the Big Bang, a fraction of today's age.
And they're enormous.
So billion solar mass black holes, these behemoths, had to be in place when the universe was about 550 million years old.
Now you have a problem, because you have to grow something really big, really fast. And you are bumping up against sort of physical limits.
Whether a black hole is nibbling or gulping down its meal, it turns out that accretion, how black holes feed, has a speed limit. Named after English astronomer Arthur Eddington, the Eddington limit will not allow a black hole to feed too fast because of the light blasting out from its own accretion disk.
Light has a pressure. So photons can impart a force on something. We see this in winds from stars. Light is pushing out gas. So there's a limit to how fast you can feed a black hole before its own luminosity quenches its own growth.
So given the speed limit, how did early supermassives, quasars, get so big so fast? Could there be a way to bypass the speed limit entirely?
The problem is still time itself. How do you grow them to 1 billion times the mass of the sun? What are the conditions that you need for that kind of growth?
Some scientists are now asking, what if there's a way to create a black hole that's already much more massive from birth, giving it a head start?
If there was a physical mechanism that would allow you to make a black hole seed, which was much more massive from the get-go, then the timing crunch is not as much of an issue and the growing problem is not as acute.
The answer, some believe, is to create a black hole directly from a cloud of gas, a scenario called direct collapse. It starts with gas clouds made of hydrogen, helium, and other elements, the same raw materials from which stars are born.
The denser clouds will start to collapse under their own gravity. And as they collapse, parts that are more dense will collapse more quickly. And so what happens is the cloud fragments.
Those fragments continue collapsing until the hydrogen atoms within them begin to merge. Nuclear fusion begins and stars are created. But what if a giant gas cloud collapsed without making stars?
We realized that there are a set of physical conditions that would allow you to form a very large gas disk prior to the formation of any stars. So this gas disk starts getting unstable. That would allow the mass to sort of flow into the center very, very rapidly and make a very massive black hole.
It's something we've all seen in nature. From tornadoes to bathtubs, a vortex, but on a supermassive scale.
If you're in a bathtub and you pull the plug out and you see the water flowing in a vortex very fast down to the center, that's exactly what happens.
Direct collapse might be a way to create very large black holes early in the universe from enormous gas clouds, completely skipping the star stage. Because they would be so large already at birth, these direct collapse black holes would have a head start, helping them to quickly grow into the enormous young supermassives we see in the distant universe.
You could potentially have these direct collapse black holes. So black holes whose original masses, seed masses, the initial masses, are about 10,000 to maybe 100,000 times the mass of the sun, and that they form from the get-go with that mass.
Direct collapse may explain how enormous early supermassives got their start.
But there's another fundamental question about supermassives. What is their role in the universe? Is their existence just a matter of chance? Or are they connected in some larger way to the very structure of the cosmos? Supermassive black holes don't exist in isolation. They seem to live in partnership with galaxies.
Collections of millions, billions, or even trillions of stars bound together by gravity. Galaxies are the fundamental building blocks of our universe. So are the supermassive black holes at their centers somehow fundamental to their very existence?
We now just assume every galaxy, even ones we have yet to confirm, will have a supermassive black hole in their center.
It could be that instead of simply being oddities, that they are a key component to galaxies, a key component to the universe.
We've come in a very short time to realize that they likely inhabit the centers of all the galaxies. That can really only happen if there's some symbiotic relationship between the evolution of a galaxy and the supermassive black hole in its core.
What could that relationship be? One intriguing clue relates to size.
The bigger the galaxy is, the more massive the black hole appears to be. So these black holes at the center seem to know about their larger scale environment.
So which comes first, the galaxy or the supermassive black hole? It's not that simple. It appears they somehow grow in tandem.
It's hard for one to form first and affect the other. So today, we think that whatever formed one had to form the other as a byproduct of that process. And that there has to be some feedback mechanism between the black hole and the galaxy that keeps the growth of the two in lock sync.
The way galaxies grow is by forming new stars from clouds of hydrogen gas.
Gas is essentially the fuel for star formation, just like gas is the fuel for our cars. And so if you run out of gas, you run out of new stars.
So are supermassive black holes somehow interfering with star formation?
When a black hole is growing, a tremendous amount of energy is being liberated and sent out into the galaxy. And so we think that some of that energy goes to warm up gas. And gas that's too warm will not form stars anymore.
The heat produced by a growing black hole makes it impossible for stars to form nearby.
And so one way that a growing black hole can influence its host galaxy is by quenching the star formation.
In effect, the growth of the supermassive determines whether or not its host galaxy grows or stagnates.
They have a kind of eating phase and then a quiescent phase. So they seem to be involved with the formation of the galaxy in that way, and then stabilizing of the galaxy at the same time.
So these mysterious supermassives may actually control the building of the universe. Not so much by their size, but by the way the energy they generate shapes galaxies.
By mass, if you count up all the black holes in the universe, the tiny ones as well as the supermassive ones, the ultramassive ones, black holes are nothing. However, energetically, how much power the galaxy gets and at what time as it assembles seems to be dictated by the central black hole. So they might well be the key players in the universe.
In the next 2 years, NASA plans to launch the James Webb Space Telescope. Humanity's most powerful telescope ever, the James Webb is designed to look in the infrared, allowing it to see farther back in time than Hubble, getting a look at the first stars and galaxies that formed after the Big Bang. Hopes are high that the James Webb Space Telescope will help solve many of the remaining mysteries about the earliest supermassive black holes.
The James Webb Space Telescope is tuned specifically to observe the early universe when galaxies were being born. It could give us deeper understanding of how you end up with a supermassive black hole in your galaxy to begin with.
Technology is moving really fast, and as a result, we have really fundamental new views of the universe. I think we are really living in a golden era of astronomy.
And the James Webb Space Telescope isn't the only new development that promises to solve some of the mysteries around black holes. A group of scientists led by Shep Dolman is now attempting the impossible, to take a picture of a black hole.
It's interesting that we can say something about the accretion flow near the black hole at all.
And if some of this linear behavior survives, maybe we'll have a way of interpreting it.
The project is called the Event Horizon Telescope.
The basic goal of the Event Horizon Telescope is really to see the unseeable. It's to bring into focus something that science has told us for many, many years is precisely something we can't observe, the black hole.
Their primary target is Sagittarius A star, the supermassive in the center of our Milky Way galaxy. They're using a global network of radio telescopes.
We need good weather at 8 different telescopes all around the world, and that is a tall order.
But if black holes are invisible, what exactly do they hope to photograph?
What we're trying to photograph really is the shadow. So as this gas around the black hole swirls inwards and actually hits the event horizon, it leaves a silhouette, a very well-defined shadow on the surrounding light. So really it should look like a donut with its very well-defined hole. And that's the picture that we are after.
I convert that into frequencies, I get a 2 pi square there.
The team has conducted their first observing run and is processing the data now.
Can you say the velocity?
It's hoped that these new technologies will give us an unprecedented view of black holes in our universe. But there is one new technology that is already delivering results. And that brings us back here to LIGO, the key player in the black hole drama, to an idea that took root way ahead of its time: gravitational waves. With general relativity, his theory of gravity, Einstein predicts that when an object moves, it can create ripples in space and time, an actual squeezing and stretching of space itself. One of the holy grails of 20th century physics was to detect these gravitational waves.
That was not easy to do with general relativity because all the effects that you could think of were infinitesimally small, very, very difficult to measure.
The thinking was, if gravitational waves could be measured, it would confirm Einstein's prediction. And there could be an added benefit. It might also prove the existence of black holes and help solve the mystery of how supermassives grow. But how to detect gravitational waves? In 1970, the problem caught the attention of a young experimental physicist, Ray Weiss. Ray had the perfect background to hunt for gravitational waves. For decades, he'd been working with more familiar waves, sound waves.
We were immigrants, we were German Jews, and a lot of our friends were very, very interested in music.
Ray devoted himself to coaxing every subtle nuance he could out of recorded music.
Those records had a terrible problem. When the music was loud, it sounded wonderful. When the music was real quiet and slow, what you heard was this shh, like that, hissing noise. And that was so annoying.
The lessons he learned trying to eliminate noise in recordings will pay off later when Ray turns his attention to detecting gravitational waves.
You have to understand how a gravitational wave does its dirty work.
As a physics problem, gravitational waves are not unlike sound waves.
Suppose the wave comes from something that is in some way moving and oscillating.
A sound wave compresses and expands air. A gravitational wave compresses and expands space and everything in it.
If that wave came through the Earth, it would cause space to expand momentarily and then contract again. It keeps doing it. It's a thing that goes bloop, 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 bloop. I don't like that.
So how to measure the extremely tiny expansion and contraction of space? Ray's idea was to use light. Send a beam of light from one place to another and measure the time it takes to get there. That's how the exact distance to the moon was calculated, bouncing a laser beam from the Earth off a mirror left behind by Apollo 11 astronauts. From the duration of the round trip, scientists could determine the distance. Ray came up with an ingenious design for an instrument that uses lasers and mirrors to detect the faint expansions and contractions of space that would be caused by a gravitational wave. It's called a laser interferometer. It works by firing a laser into a splitter. Half of the light continues straight ahead towards one mirror, while the other half is sent towards another mirror. The distant mirrors bounce the light beams back, where they rejoin at a photodetector. If the distances the two beams travel are exactly the same, the system is designed so the two beams cancel each other out. The detector sees nothing.
You set the trap to measure the gravitational wave. Now comes a gravitational wave that's coming, let's say, at this structure.
If a gravitational wave passes through, it briefly changes the length of the arms. The light beams no longer arrive back at the same time to cancel each other out. A gravitational wave hits, light appears at the detector. The trap has sprung.
That's the basic idea. It's a very straightforward measurement.
A clever idea and simple in principle. But the devil and the Nobel Prize lie in the details. The difference in length between the two arms would be tiny beyond imagining.
How tiny? We'll take the size of an atom. It's less than that. Go down by a factor of 100,000. That's the nucleus of an atom. It's less than that. It was 100 times below that. So we're talking about really itsy bitsy teeny weeny. I thought it was crazy. I think everybody's initial reaction to the idea was, this is going to be impossible.
In 1973, Kip Thorne puts his skepticism on the record in a classic textbook, doubting it will ever work. But Kip has never heard Ray Weiss explain his plan in detail. And when he does...
We spent the whole night talking. And so I said, no, it's very possible. And within no time at all, 20 minutes, maybe half an hour, Kip was solidly understanding this thing. He says, yep.
And I ate crow the rest of my career because once I had talked with Ray about it in detail, I decided I would spend a large fraction of the rest of my career helping the experimenters.
But it will take 40 years and enormous sums of money to bring Ray and Kip's vision to reality.
Getting LIGO funded was extremely controversial. Hundreds of millions of dollars to detect a signal that had never been seen before. There were many people who feared that LIGO would suck the money out of the room. And so there was a lot of controversy. What everybody could agree on was this was extremely difficult.
With such a sensitive instrument, one of the biggest challenges is Ray Weiss's old hi-fi nemesis, noise.
Ground motion, the seismic motion of the earth, acoustics noise, sound, everything would tend to move that mirror.
Turns out, even the emptiness of a total vacuum creates a potentially crippling problem. At subatomic distances, the weird randomness of the quantum world causes a ruckus in the mirrors.
This quantum noise is due to quantum fluctuations. These mirrors are doing what an electron does inside an atom. They're jiggling around.
Exquisite sensitivity, extreme vacuum, hundreds of thousands of electronic circuits. LIGO is one of the most complex instruments in the history of science. And as a final means of eliminating false signals, they build not one, but two complete installations. One in Washington State and another in Louisiana.
And so the LIGO designers did it right. They designed more than one detector, separated from one another by great distances, so that if you detect something in one and not in the other, then, go back and check your electronics. Check to see if it was April Fool's Day and somebody didn't just tweak the knobs.
Early fall 2015. Both locations are operating, but the first official science run has not yet begun. They're still testing. In the early hours of Sunday, September 14th, 2015, a scientist in Louisiana makes a fateful decision. Robert Schofield has been working all weekend, doing final calibrations.
Alrighty, let's take a spectrum.
He has one last test.
So let's see where this computer is getting its power.
But it's late, and the equipment is not cooperating.
It was about 4 or so in the morning, and we still had about another hour of work to do. And we were like, yeah, things aren't working so well, and I'm really tired. Let's not do this last hour or so of work.
They call it a night, and 40 minutes later, in the silence of their inactivity, they open the door to history. powerful gravitational wave rumbles through both detectors, Louisiana and Washington. Had Robert Schofield worked 40 more minutes that night with the instruments in test mode, a signal that had been on its way for 1.3 billion years would never have been recorded.
I like to say, you know, one of my biggest contributions to LIGO has been my laziness that day.
I got an email from somebody here saying, hey, you look at this place on the web. I looked at that and I said, holy.
It was so strong that you could see it by eye in the data. It was too good to be true.
But it was true. In fact, it was loud and surprisingly clear.
And it just sang at you. The stair was standing up.
The signal lasted less than a second. But in that briefest of moments, it delivered a cosmically profound message more than 1 billion years in the making, proving the existence of black holes.
So what we saw in the signal involved oscillations of the mirrors that were slow at first, became faster and faster and faster. And this was precisely the kind of behavior that you would expect from gravitational waves caused by two black holes going around each other, spiraling together.
Two massive black holes, one 29 times the mass of the sun, the other 36 times the mass of the sun, whipping around each other hundreds of times a second, finally completing their act of mutual destruction by merging, creating a single, larger black hole of 62 solar masses. The violent merger converts some of the mass into an apocalyptic release of energy beyond anything ever before witnessed.
The collision, in effect, creates a veritable storm in the fabric or the shape of space and time. It's as though you had taken 3 suns, you had annihilated them completely, converted it into gravitational waves. The power was 50 times higher than the output power of all the stars in the universe put together, in a fraction of a second. But the most powerful explosion that humans have ever had any evidence for, with the exception of the Big Bang.
Since that very first signal in September 2015, LIGO has detected several more collisions of black holes. In October 2017, Ray Weiss, Kip Thorne, and LIGO's former director Barry Barish received the Nobel Prize. The LIGO discoveries prove that black holes can merge. One way they can grow bigger quickly.
More and more evidence of these merging black holes tells us there are a lot of these stellar black holes around that they can find each other and merge.
And the discovery opened an entirely new way of observing the universe.
We've always thought of astronomy as an observational field where we are looking at radiation. We are seeing things. But this is not radiation. This is something much more fundamental. These are sort of fundamental tremors in space-time itself. We can now hear the universe.
For the first time, astronomers have simultaneously seen and heard a cosmic event. In August 2017, LIGO detected gravitational waves from a collision of 2 neutron stars. Black holes are empty space, but neutron stars are dense, dead stars that can crash together and light up the skies. When telescopes and satellites around the globe pointed in the direction of the sound, the world saw fireworks in an explosive collision and afterglow. Possibly, the collision resulted in the creation of a new black hole. But unless we observe the formation of a black hole, there is much we will never know. Because so much about black holes is irretrievably out of our reach, we can never know where they came from, what's inside, or their history. But we can imagine their future. The number of black holes in the universe is increasing, and they're getting bigger. Stars collapse, black holes feed and merge, new ones form. Could it be that one day everything will end up inside them and they will rule the universe? Untold trillions upon trillions of years after this happens, and the last bits of matter cross their event horizons, black holes themselves may radiate away and vanish from this reality. Their mysteries are many, and we're just starting to unlock the secrets of these strange, powerful places. But one thing is certain, black holes will continue to intrigue us, tantalize us, and challenge both our science and our imaginations.
Earth, a 4.5 billion-year-old planet, still evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede, the Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, an investigation into California's San Andreas Fault, the greatest fault line on Earth. 800 miles long, this ugly scar on the landscape has spawned earthquake after earthquake. But for now, it waits quietly, deep under our cities, building up stress to strike once again. The San Andreas Fault is one of the most dangerous geological features on Earth. California's greatest cities and millions of her citizens live in constant peril. Since records began, there have been 13 large earthquakes along the San Andreas Fault.
Water lines will rupture and there is no water coming out of the fire hydrant.
And now, America's geologists, her rock detectives, are warning of a potential disaster.
Major damage has been done.
In the fall of 2008, more than 300 scientists calculated what a major earthquake would do to Southern California.
We've been conducting a special study of a magnitude 7.8 earthquake on the southern San Andreas Fault, large enough to potentially damage tall buildings. Fire will be very significant.
The definitive scientific report presented to politicians was codenamed Shakeout. It forecast thousands of deaths and billions of dollars of damage in the city of Los Angeles, which makes it crucial to investigate the most important question: when will the next big earthquake hit the San Andreas Fault? The latest preparations for disaster are the climax of an investigation that started more than 100 years ago. In the aftermath of the great San Francisco earthquake of 1906. The earthquake struck on a Wednesday, just before dawn. The ground shook violently for 45 seconds, igniting fires that raged unchecked for the next 4 days. "28,000 buildings, a tenth of the entire city, were destroyed, and more than 3,000 people, 1 in every 100 of the population, were killed. With a magnitude of 7.8, it's in the top 20 of North America's strongest ever earthquakes. The scale of the Great San Francisco earthquake shocked the nation. But no one understood what had made the city shake. Native American myths explained earthquakes as shocks from a battle between warring spirits. Latter-day explorers couldn't understand the shocks that destroyed their mission buildings. One Spanish missionary wrote, "The earth shook around me from explosions under the ground." 300 years later, and science has still made little progress. Refugees in the ruins of San Francisco still blamed earthquakes on mysterious underground explosions. So, just 3 days after the earthquake, the state of California asked one of the world's most famous geologists, Andrew Lawson from California State University, to investigate what had destroyed the city. He and a team of 25 scientists began collecting damage evidence in the city and surrounding countryside. There were roads that had buckled, rail tracks that had twisted. The most startling evidence of all, that came near the town of Bolinas in Marin County, to the north of San Francisco. This picket fence had an 8-foot gap in the middle. Before the earthquake, it was a solid boundary fence dividing 2 fields. But when he recreated what had happened, Lawson realized that the land had jolted apart and torn the fence in 2. Plotting the evidence on a map around San Francisco revealed a surprising pattern. Because connecting the dots drew a straight line. And at every point, the earth moved in the same way, on the coast to the north, inland to the south. This line of weakness was the culprit they were searching for. South of San Francisco, the suspect line ran underneath a lake, the Laguna de San Andreas. So now, the earthquake perpetrator at last had a name. Professor Lawson, who a decade earlier had identified cracks in the earth here as a harmless rift, now rechristened it the San Andreas Fault. In modern-day San Francisco, the buildings, the roads, and the railways have long since been repaired. But if you know where to look, evidence of the 1906 quake can still be found. Geologist Charlie Paul follows in the footsteps of Lawson's team, seeking signs of the havoc from 1906. He finds it on the cliffs at Muscle Rock, 12 miles south of San Francisco.
The cliff is not here by accident. There's a very good reason why this cliff is here. Half a mile or so of the shore face apparently fell off in the 1906 earthquake. And if you look down below us, there's a big rotated block that's near the present-day shoreline. And it is just inboard of the San Andreas Fault. The San Andreas Fault is about a quarter of a mile offshore here. And of course, that's one of the major crustal junctions on this side of North America.
Modern computers can now trace how damage waves spread out across the city, and that pinpoints where the quake originated along the San Andreas. It was offshore, about 2 miles out to sea from the Golden Gate Bridge. So, to continue tracking the fault, the investigation must head out to sea. Marine geologists use remote operating vehicles, mini-submarines, to map the seafloor.
What you'd see is subtle variations in the topography, or topography that would not naturally line up. So there might be a line on the ocean floor that is higher or lower on one side, and you can use various techniques to determine that this actually is a fault instead of some other process.
Running south across the seabed, the San Andreas finally runs out of ocean and hits the land. This broken line of rocks, stretching in from the sea, marks where the San Andreas hits land 12 miles south of San Francisco.
We're here at Muscle Rock, and we're essentially standing on the San Andreas Fault right now. And if there was an earthquake, I don't know what would happen right here, but I wouldn't want to be here.
This Pacific coastline, where cliffs crumble slowly into the sea, is the boundary between two of the Earth's massive continental plates. Separated by the San Andreas Fault, two vast separate blocks of the Earth's crust lie directly alongside each other. Here, the continent of North America lies slightly on top of the adjacent section of crust which holds the Pacific Ocean. The join can be seen where these lower, darker rocks are overlaid by light-colored sedimentary rocks.
These rock types differ by more than 100 million years in age. Two rock bodies that are not similar in any way have been brought together.
The fault line was exposed to geologists when the cliffs collapsed here in the 1906 earthquake. But back then, nobody understood how and why the two different types of rock were next to each other. Until around 40 years ago, when the answer was finally revealed by the theory of plate tectonics. The theory showed that the Earth's crust consists of separate moving plates on which the oceans and continents sit. Around 200 million years ago, the heavy Pacific Ocean plate collided with North America and started sinking underneath the lighter continent. Professor of Geophysics Mark Zoback studies that process, called subduction, in his laboratory at Stanford University.
For many millions of years prior to the existence of the San Andreas Fault, the Pacific Plate was subducting beneath North America. The oceanic plate was diving down, and that process went on for, well over 100 million years. So a tremendous amount of activity was occurring.
As the unstoppable force of one plate met the immovable object of the other, they were forced to change direction.
About 20 million years ago, the plate motions were such that the Pacific Plate had to start sliding north with respect to North America. And now, you know, the principal motion is this sliding process between the two plates. And 20 million years ago, the San Andreas Fault was born.
It was the moving plates that crushed different types of rock together, just as here at Muscle Rock. At last, the investigation knows what it is dealing with. The San Andreas Fault is 800 miles long, emerging from the seabed north of Point Arena in Northern California and running down to the Salton Sea in the south. The evidence is coming together. Clues from the 1906 earthquake, such as the picket fence that was torn apart, prove that the land was moving. Connecting the dots identifies the straight line of the San Andreas Fault. And Muscle Rock uncovers different plates of the Earth's crust on either side of the fault line. But investigators still need more information about how often the San Andreas has spawned earthquakes in the past. It might help them answer the all-important question: when will the San Andreas strike again? To discover when the San Andreas Fault will strike again, the investigation needs to know about ancient earthquakes that have struck along the fault line. But there's an immediate problem.
Well, here in California, it's a particular challenge. Some of the earliest written records were from the missions and from the early explorers, so only dating back into the 18th century here. Other parts of the world, we have an earthquake history going back millennia.
The investigation moves 350 miles south of San Francisco to a desert where the San Andreas may have been active for thousands of years. There's crucial evidence here about earthquakes from ancient times.
This creek used to flow straight across the San Andreas Fault here, but several earthquakes formed a natural dam where the San Andreas Fault wedges up here in front of me. That created a small pond, and now we're looking at the dry sediments of that pond that record the history of earthquakes, and that tells us quite a great deal about the past behavior of the San Andreas Fault.
Some of the clues are so small that Hudnut's detective work gets him down and dusty among tiny cracks inside the fault.
Sometimes we can find out about the past behavior of the San Andreas Fault by looking at the tiniest details.
At the bottom of this small ancient pond, mud sediments collected above a fine line of pebbles. Then, an earthquake shifted the land upwards on one side of the vertical fault line.
So this layer was originally flat, and then, in a subsequent earthquake, it was broken like this along this tiny fracture strand of the San Andreas Fault.
But finding proof that this is the site of an ancient earthquake is only part of the story. Hudnut needs to know how long ago it happened. The bare rock layers are no help in dating his find, but just above the fracture line of the rocks, he has found the evidence he needs.
Here, a bush was burned by a prehistoric wildfire, and that remnant of carbon is why you see this black stain on the side of the trench wall.
The key to unlocking the age of the rocks is carbon-14, known as radiocarbon. Its molecular structure means that carbon-14 is a more unstable isotope than other forms of carbon. It's absorbed by growing plants, then radioactively decays at a known rate after the plant dies. So measuring carbon-14 in vegetation burned in a wildfire reveals how long ago those plants died and dates the rock in which the carbon is found.
And through this, we can reconstruct the evidence of the past earthquakes.
Radiocarbon dating has proved that earthquakes have been happening along the line of the San Andreas for thousands of years. The particular small earthquake investigated by Hudnut, for example, is around 3,500 years old. It happened at a time when the last woolly mammoths were dying out in North America. the investigation moves to an even more remote desert spot, the Carrizo Plain, 160 miles north of Los Angeles. Here lies a dried-up riverbed, which takes an unusual course. Coming down off the hills, the creek bed takes a sudden, sharp turn to its right. A few hundred feet later, it makes an equally odd 90-degree turn to the left. The creek crossed the line of the San Andreas Fault, but early geologists were mystified. Why did it bend in this way? The scientific pioneers were limited to studies on the ground. Nowadays, Hudnut has an advantage. He can take to the air.
The San Andreas Fault, where it cuts through the Carrizo Plain, it almost looks like a scar, and it was caused by repeated earthquakes in the past.
Along the long line of hills marking the course of the San Andreas, Hudnut spots the puzzling bends that he's seeking.
Oh, if we could swoop along the fault through here, that would be awesome. Oh, there's a great angle. See that right angle offset channel with the elbow in it right there? That's a classic one right there.
Hudnut's aerial view of the creek bed shows that the river once flowed straight on across the fault. But little by little, a series of earthquakes along the San Andreas dragged the creek away from its original course. Recreating how the land had moved showed Hudnut that the two parts of the creek had traveled more than 300 feet apart.
So if you imagine the North American plate is fixed and the Pacific plate is moving to the northwest, the Wallace Creek site records that offset because the channel was straight across the fault, but it's been offset through time.
Earlier investigators had already radiocarbon dated the land on each side of the fault here, revealing that it took 3,000 years to change the creek's position. So, knowing the distance and the time it took to do it, lets Hudnut calculate the average speed with which the two land masses are moving past each other. 300 feet in 3,000 years. 1 foot per decade. Just over an inch a year. But this was never a steady, sliding, 1 inch a year movement. The reality was a series of sudden, small jumps whenever tension built up enough between the two moving plates to overcome friction between the rocks and rip the land apart with an earthquake. It's an important moment for the investigation. Knowing how fast the land is moving not only reveals the stress that's building up, but also the risk of an earthquake. The San Andreas Fault is giving up its secrets. Clues from a long dried-up pond reveal the site of ancient earthquakes. Carbon from a prehistoric fire provides the dates. And bends in a riverbed prove how fast the plates are moving along the San Andreas. But now the investigation has a new mystery to solve. If the land along the San Andreas is moving 1 inch every year, causing earthquakes, then why has one small town along the fault line never had any? The investigation has discovered how fast the land is stretching and straining along each side of the San Andreas Fault, which should help establish when that ever-increasing stress will snap the land apart in the next major earthquake. But there's a problem. One part of the fault line just doesn't fit the pattern. The small town of Hollister is unique along the San Andreas Fault system. It's never had an earthquake, and the investigation is going to find out why. Hollister has a population of 37,000, And nothing here is quite the way it should be. There are plenty of clues suggesting that the land must be moving here. Sidewalks with cracks in, curbstones way out of line, and walls that are bent out of shape.
Walking through Hollister, we can see anything that man has built that was laid out in a straight line may have a jog in it. Every year it changes a little bit, and it's a progressive thing.
The clues add up to one clear conclusion. Even without any earthquakes, the earth in this town, in the heart of the San Andreas system, still slides imperceptibly slowly and effortlessly along.
In one sense, the damage that you see here associated with the creeping is clearly sort of under control. But as a geologist, if you start playing that out for tens of thousands or hundreds of thousands or millions of years, the consequences of that become enormous.
For many years, the creeping ground that moved without earthquakes remained an unsolved mystery. But then, the investigation moved 100 miles south to another small community where the land also creeps along. The village of Parkfield has a population of just 37 people and a bridge which spans right across the San Andreas Fault. The bridge separates the Pacific Plate on one side from the North American Plate on the other. And the bridge railings have started to bend.
I'm right now on the Pacific Plate on the west side of the San Andreas Fault. And, you know, the San Andreas comes off the flank of that hill and right across that field, right under the bridge, and then right over by the corner of that building or that fence post, and then on off to Middle Mountain.
The movement here around the bridge is strikingly similar to the slow creeping ground of Hollister. But there is one important difference here in Parkfield. Every couple of decades or so, this village does have earthquakes. They're just little tremors, but they're big enough to be recorded on earthquake monitoring seismographs. That's why the village proudly boasts of being the earthquake capital of the world. But it's perhaps more accurately called the earthquake study capital, because scientists are fascinated by the fact that earthquakes here follow a predictable pattern. Elsewhere, earthquakes always strike without warning. The toll of death and destruction made worse because nobody knew they were coming. So scientists are desperate for any clues that might help predict when an earthquake could happen. And here in Parkfield, the earthquakes happen with astonishing regularity, on average every couple of decades or so. Minor quakes happened here in 1857, 1881, 1901, 1922, 1934, and 1966. After the 66 earthquake, investigators set up a network of monitoring instruments to see if the fault gave any warning before the next earthquake arrived. They expected it sometime between 1988 and 1993, but it was late, and months of waiting stretched into years. But still, the scientists waited, until finally, in December 2004, the long-awaited earthquake arrived and was caught on film from a now slightly worn and damaged camera. The earthquake movie may not have seemed that impressive, but the instruments collected a mass of information. The data didn't, after all, help with earthquake prediction, but it did pinpoint where the earthquake started underground, which told investigators where to look next. Deep down under the Parkfield countryside, Starting slightly to one side of the fault, the aim was to angle in and stab into the very heart of the San Andreas. After 3 years of drilling, long cores of rock were extracted from the exact spot where the earthquake occurred. This was the first time that team leader geologist Mark Zoback had ever seen rocks from the center of the San Andreas.
What we're looking at here are cores from the active San Andreas Fault from a depth of about 2 miles. So for the earth science community, these are like moon rocks. As we were trying to exhume these cores, we had a great deal of drilling difficulty. The San Andreas Fault was literally fighting back. After 9 weeks of attempting to recover the cores, in the middle of a huge lightning storm, almost a scene directly out of Hollywood, with the thunder and lightning, these cores came to the surface. And so it was a tremendous feeling of satisfaction. The lightning and thunder just made it that much more dramatic. And we're all wearing gloves. We didn't want any oil from our fingers to affect the core. And the rule was that you touch the core as little as possible, obviously.
I'm not gonna wait for you guys. Oh, look at this beautiful rock.
The reality was we couldn't help ourselves, and it was just such a remarkable thing to be actually looking at the San Andreas Fault for the very first time that we all got to touch it a little bit.
Buried within the rock cores, they found a vital clue about the way that land slips along the San Andreas. They found serpentinite.
Serpentinite is an unusual rock type. It was originally formed at the base of the ocean crust and exhumed up onto the continent. But the reason that serpentinite is so interesting is that serpentinite is very easily altered to talc. It allows the rock to slide at very low force levels. Talcum powder is very slippery.
Talc's crystalline structure of soft, sliding, flat plates makes it one of the slipperiest rocks known to science.
So talc could well be a key mineral in deciding how the fault is actually working in Central California. We see that the secret of the slipping San Andreas Fault is actually the rocks themselves.
The talc explains the tiny earthquakes of Parkfield. Nobody's yet drilled to investigate the rocks at Hollister, but scientists suspect the talc is present there too. Cracks in the wall show the land creeps in Hollister. And a bend in the bridge reveals the same creeping ground in a nearby town. Rock cores extracted from the fault contain serpentinite, leading investigators to the softest and slipperiest mineral, talc, which lubricates some parts of the fault. The investigation is having success, but one crucial question remains to be answered. What will the San Andreas Fault do next? The investigation into the San Andreas Fault is trying to predict when and where its next major earthquake will strike. So far, the only certain prediction is the far distant future of the San Andreas. Look 20 million years ahead. If the plate movements continue to follow their pattern, Los Angeles will end up becoming a suburb of San Francisco. But predictions on a shorter time scale are more difficult.
If you were to ask the question, can we predict earthquakes? My answer would be no, because I know what your question really meant is, can we predict that an earthquake is going to occur on a certain fault at a certain time that we can specify in the future? And we cannot do that. But there are many things we can predict. We can predict which faults are likely to produce the big earthquakes. We can predict how big the earthquakes are likely to be, and we can even predict the probability of the earthquake occurrence over some period of several decades.
Predictions are most crucial where the San Andreas runs to the south of LA. Here in the Coachella Valley Desert, geological evidence of earthquakes stretches back 1,500 years and more. And they follow a regular pattern. Major earthquakes strike here with monotonous regularity every 200 years. But the latest one is long overdue. There hasn't been an earthquake here for more than 300 years. That's a concern, because parts of the San Andreas Fault system run straight from here towards the city of Los Angeles. The faults will transmit earthquake shocks in a straight line towards California's biggest city. Geologist Yuri Fialko regularly monitors how the ground moves on either side of the fault line. He lines up his GPS equipment precisely over a series of metal pegs fixed into the ground.
This information is crucial for estimating how fast the fault slips at depths and what is the rate of accumulation of strain in the crust. In other words, how close the crust is brought to failure by a slip of the fault at depths.
The repeated ultra-precise measurements reveal that land here, on the surface, hardly moves at all. This is a problem, because deep underground, the stresses and strains are still building up.
The fault is moving at depths at a fairly high speed, and this deformation is growing and growing and growing with time.
Miles underground, the deep fault is moving at more than an inch a year, which tells Fialko that in the centuries since the last quake, the surface should have shifted 300 inches, 25 feet or more. But it hasn't. So sooner or later, something's gotta give. And Fialko knows what that something will be. The rocks themselves.
And one example is this type of rock, which is called granite, or this is in fact the rock out of which most of the Earth's crust is made.
A microscope reveals the crystalline structure of the granite. The crystals make the rocks tough, but they have a hidden weakness. The bonds between them may suddenly crack under stress.
Basically, once this material solidifies, it is able to crack and be sheared on the fault surface. And the brittle behavior of these rocks is what lies behind the physics of earthquakes.
Granite rocks underlie all of the San Andreas Fault, but right here, the rock's under greater stress than anywhere else because it's so many centuries since a major quake occurred.
And now we're over the 300-year limit, and so it means that the amount of strain that has been accumulated on the fault at this point is very close to the maximum strain that this fault has ever seen through its geologic record. And this is a fault that is capable of generating great destructive earthquakes.
Fialko believes the coming quake could be the big one that people have been talking about for years. And the effects could be horrific because of the population density of Southern California. When the last huge quake occurred 300 years ago, Los Angeles was just a tiny Spanish mission community with fewer than 100 people. Now it's America's second largest city, with almost 11 million people living in the earthquake-vulnerable metropolitan area.
People who live in California probably experience a small or moderate-sized earthquake every year. A few things moving in your house, but it's really actually kind of fun. There is no major destruction. People just go on with their life. Much bigger events, on the other hand, are quite a bit different story.
With the threat to Los Angeles becoming ever clearer, the investigation is nearing its conclusion. Data from repeated GPS measurements in the desert reveal evidence that stress is building up, while examination of the rocks of the crust show they may not take the strain for much longer. All the evidence points towards a potentially huge earthquake building up in Southern California. And new experiments suggest the coming quake could be far worse than anyone had ever imagined. There is new urgency in the investigation into the San Andreas Fault, as revealed by recent evidence compiled by 300 of America's most respected scientists. They warn that Los Angeles will be devastated if a major quake strikes along the southern section of the fault line. While there hasn't been a major quake for hundreds of years, even small ones can still be deadly. Like the Northridge earthquake, which struck this LA suburb in 1994. Rupturing along an offshoot of the main San Andreas Fault, the quake was only a magnitude 6.7, considered moderate on the scale of earthquake measurement. But it still killed 72 people and injured 12,000 more. And new evidence suggests Mother Nature might have a lot more in store for Los Angeles. Scientists have long known that earthquakes generate several distinct sets of waves. They travel at different speeds, each spreading damage and destruction out from the epicenter. Modern city buildings in earthquake-prone areas like California are engineered to cope with such waves. Now, new research by geophysicist Professor Aris Razakis suggests that the San Andreas may offer a new and even more deadly threat. Razakis researches how earthquakes rupture along straight-line faults, just like the San Andreas, where it approaches Los Angeles. He creates his own mini-earthquakes, representing the San Andreas Fault, by a hairline crack in a thick, transparent block. This special material shows up internal stress lines when it's lit by a laser. And the earthquake is triggered by a tiny explosion.
3, 2, 1, 0. The load has dropped. And the explosion was big enough that we even have a crack.
An ultra-high-speed camera capturing 10 million frames a second reveals a startling and newly discovered phenomenon. This frozen picture reveals stress lines speeding along the mini San Andreas in the milliseconds after the explosion. The cone to the left of this frame is a previously unrecognized type of shockwave racing along the rupture line from the earthquake's center. On a microscopic scale, it looks and moves exactly like the sonic boom produced when a supersonic aircraft such as Concorde breaks the sound barrier.
Because we also see map cones, lines that are emitted from the rupture tips as from the tips of moving airplanes.
And just like a sonic boom, it can be dangerous.
In the same sense that we hear the sonic boom from the Concorde, you're going to feel the sonic boom from the rupture.
The danger comes because many high-rises just aren't built to cope with extra stress from this newly discovered type of shockwave.
So if you are an old building, for example, you will take one wave, you will accumulate some damage, and very soon after that, you will get very strong ground shaking because of other types of waves coming also.
The high-speed ruptures that Razakis calls super shear happen where faults run in a straight line, which might help explain a 100-year-old mystery surrounding the Great San Francisco Quake, the natural disaster which launched the entire San Andreas investigation. The overwhelming damage in San Francisco has long seemed surprisingly out of proportion to the 7.8 magnitude of the quake. And there's a particularly straight section of the San Andreas approaching San Francisco. So many scientists now believe that the damage was greater than expected because the 1906 quake had traveled at super shear speed. Of greater concern to modern emergency services is not what happened a century ago, but what could happen tomorrow. Because there is a similar straight section of faulted ground heading straight towards Los Angeles. And if a super shear earthquake develops on that line, then the consequences could be disastrous. All of the investigation's warnings about the San Andreas came together in the fall of 2008 with the biggest earthquake drill ever held in California.
If this earthquake would have happened in reality, there would have been buildings coming down. We know that there would be no water now in certain areas. So that's what this exercise is all about.
But what are the real chances of Los Angeles soon being hit by a massive earthquake? Frighteningly, the best scientific consensus now warns that there's a 99% chance of a major quake in Southern California within the next 30 years. To better understand the threat to LA, the geologists produced their study jointly with experts in charge of the city's disaster planning. And none of them doubt that the big quake is coming.
It really isn't even a question of if anymore. The shaking is going to be severe for 2 to 3 minutes. And then it's going to stop. And then you're going to have that moment of silence that often happens before you start hearing the car alarms and all those other sounds that you have in a disaster like this.
The study estimates that a major earthquake in the LA metro area would cause 2,000 deaths, 50,000 injuries, and $200 billion of damage.
You're going to have conflagrations developing. Tens of blocks will be on fire.
The water lines will rupture and there is no water coming out of the fire hydrant.
That's the kind of nightmare scenario that we're looking at.
This specter of disaster to California's people and cities motivates the search to unravel the secrets of the San Andreas Fault. All the evidence is finally in. The damage reports for the 1906 disaster show the fault's 800-mile path. The different types of rock at Muscle Rock provide clues to how the fault was created 20 million years ago. The riverbeds prove how fast the land is moving. The mineral talc explains why some parts slip without major quakes. The brittle granite rocks reveal a threat to Los Angeles. And recent lab experiments uncover new and more dangerous earthquake shock waves. But one goal has eluded the rock detectives who study the greatest fault line on Earth. When will the sleeping San Andreas come to life once again? It could be any time. The only certainty is that nothing is certain in the ever-evolving story of how the Earth was made. Earth, a 4.5 billion-year-old planet, still evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede. The Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, the Marianas Trench, the deepest point on Earth, is explored. Its sheer walls cut 7 miles into the Pacific Ocean. The mystery of what created this deep, dark chasm takes science detectives on some of the most dangerous dives ever attempted. Deep into the abyss. Scouring the ocean floor, scientists uncover a strange undersea world of fiery mountains, bizarre mud volcanoes, and the largest geological structure on Earth. Discoveries from this unique underwater world will revolutionize our understanding of the powerful forces that shape not just the trench, but the Earth itself. Hidden deep beneath the waves of the Western Pacific lies the Marianas Trench, the deepest point of all the oceans. The first step on the journey of what created this mysterious scar in the Earth's crust and how it continues to mold the planet takes us back to 1872, when a British research vessel, HMS Challenger, set out on the first ever mission to map the ocean floor.
Throughout most of recorded history, men had just assumed that beyond a certain level the sea was pretty flat, pretty dead, fairly lifeless. They weren't expecting to find anything very interesting.
For 4 years, the Challenger crisscrossed the oceans, covering 70,000 miles, a third of the distance to the moon. The crew plumbed the depths every 140 miles, using a total of 249 miles of rope and hundreds of pounds of lead weight. It was tedious, backbreaking work, but at the time it was the only way to measure the depth of the ocean floor. When they got to the Western Pacific, 200 miles off the island of Guam, the crew routinely lowered the rope for a measurement. But the weight kept on dropping and dropping.
It's a big surprise. Nobody thought the ocean was this deep. So all of a sudden we've got scientists saying, why is that?
Eventually, the weight struck the bottom at 4,475 fathoms, nearly 5 miles beneath the ocean's surface.
The scientists would be going, wow, we found something, and what does it mean? Is it a little hole? Is it a big hole? What kind of feature is it down there? There's a whole lot of questions you get when you find this one spectacular reading.
The Challenger expedition marked the birth of modern oceanography and provided the first crude map of the ocean floor. It showed how the ocean floor gently slopes away from the land and then plummets thousands of feet into vast flat plains. But the Western Pacific is different. It drops off again into the 5-mile deep hole, a hole that blew right out of the water the long-held belief that the sea floor was flat and featureless. And it spawned a mystery, because nobody could understand how this strange underwater feature came about. It would be 75 years before any answers emerged. It took a revolutionary new technology, sonar, to push the investigation forward to the next crucial stage. Sonar was first developed in the early 1900s and then perfected during the 1940s to detect submarines lurking in the deep. The system works by pumping sound waves through the water. The waves bounce off solid objects and are reflected back to a detector. By measuring the time it takes for the sound waves to bounce back, scientists realized they could build a remarkably accurate picture of the world beneath the waves.
The world's major navies spend a lot of time and effort developing submarine hunting technology. Then the hydrographers discover that you can use this to chart the bottom of the sea. And it's an awful lot cheaper and easier than using large numbers of sailors pulling on ropes.
In 1951, a British Navy research ship returned to the deep hole found by the Challenger expedition. But this time, they were armed with sophisticated new sonar equipment. And the results were amazing. Detailed sonar maps revealed that the deep hole in the Pacific Ocean floor isn't a hole at all, but part of a massive trench, 30 times deeper than the Empire State Building is high. It runs twice the length of California, 1,500 miles from the southeast of Guam to the northwest of the Mariana Islands.
People were probably astounded by what they were seeing because clearly the ocean floor had enormous changes in relief, was very mountainous in some places, had great deeps in other places. To a geologist, this would be extremely exciting.
Even within the trench itself, there are remarkable variations. At its southern end lies the greatest surprise of all. The seafloor drops down another 2 miles to its lowest point, a staggering 7 miles beneath the waves. Scientists had discovered the deepest part of the oceans. Even today, it is the lowest known point on the planet. They named this part of the trench the Challenger Deep in honor of the ship that discovered it.
To get a sense of just how deep trenches are, if we take the height of Mount Everest, we would still have about a mile of water above us before we get to the ocean's surface.
But how the Marianas Trench was formed remained a mystery. Investigators decided the best way to find the answer was to dive to the bottom of the trench, to see for themselves the lowest point on the planet, the Challenger Deep. But they faced a major problem. At the bottom of the trench, they would have to contend with pressure 1,000 times stronger than at the surface. That's the equivalent of being squeezed on all sides by the weight of 50 jumbo jets. To demonstrate the effects of such pressure, scientists use a dummy head.
Today what we're going to do is actually put one of these styrofoam wig heads in the pressure chamber and expose it to the pressure we would see in the Marianas Trench. That's about 16,000 psi.
A human skull would be crushed to a pulp, but the rubbery head will only have all the air squeezed out.
Wow, that's smaller. And here's what the original size was, just for comparison. Quite dramatic. Pretty stark difference between something that hasn't been 7 miles deep in the ocean and something that has. Glad I'm not going there. At the Mariana Trench, human life is impossible. We're not equipped to resist those kinds of pressures. And so it's necessary to protect humans from that type of an environment.
The challenge to engineers was how to accomplish this. In 1953, Swiss scientist Auguste Piccard designed the Trieste, a pioneering vehicle that could withstand the crushing pressures. The submersible was dominated by a 50-foot-long hull, filled with light aviation gasoline and lead weights to control buoyancy. Slung underneath it was a tiny 6-foot spherical cabin with 5-inch thick steel walls. Finally, after 7 years of modifications and manned test dives no deeper than 3.5 miles, the Trieste was ready to attempt the 7 miles to the bottom of the trench. The commander of this perilous undertaking was U.S. Navy Lieutenant and deep-sea explorer Don Walsh.
I know the astronauts that go through this all the time. Why do you have to be there? Why can't we just put up a robot to do things? Got to be there because that's what we do.
Only a few officers and scientists knew about the risky mission, which was launched in January 1960 from the western Pacific island of Guam.
Guam, in those days, was kind of a backwater. It was just right for us because we were trying to do this project sort of out of sight because we weren't too sure it was going to work. The Navy just didn't want to be embarrassed by a failed science spectacular.
Accompanying Walsh was the son of the Trieste designer, engineer and oceanographer Jacques Piccard. The two men would spend the next 9 hours squeezed inside the cramped sphere.
And we had had 20 cubic feet of space inside. That's about the same as a household refrigerator. And the temperature was almost that cold inside. It was a drama.
The Marianas Trench is one of the most remote, inhospitable places on Earth. In January 1960, two deep-sea explorers, Don Walsh and Jacques Piccard, plunged into its depths on board the submersible, the Trieste. At a speed of just 3 miles per hour, they began their slow descent into the twilight zone. By 3,000 feet, the darkness was total. The only illumination was from the Trieste's powerful lights.
The depths we were operating at, it was always black. The only thing that lit up the abyss was the bioluminescence from animals and plankton. Like fireflies, they carried their own light sources with them.
Encased in their 5-inch thick steel sphere, Walsh and Piccard quickly passed their test dive record of 18,000 feet. Everything appeared to be going to plan. At the rear of the cabin, the crew were protected by a double layer of glass. But 2 hours into the dive, the outer pane cracked.
We had a very big bang. We didn't know what it was. We were about 20,000 feet. And we looked around and checked everything.
Every square inch of their tiny life-supporting capsule was fighting back 8 tons of pressure. With the outer pane broken, the only thing between the men and instant death was a single pane of glass.
If the inner window had cracked, we would have been instantly dead, maybe even before we knew it.
But incredibly, the inner pane remained watertight. Walsh and Piccard decided to continue the descent. After a tense, claustrophobic 4 hours and 48 minutes, they approached the bottom of the trench, only to be startled by movement on the sea floor.
Just before we landed, we saw a flatfish about a foot long, and that's a bottom-dwelling fish, so if you see one, there are others.
Nobody expected to see life at these crushing depths, but it meant the explorers had reached their goal. The very bottom of the Marianas Trench. The depth gauge, with a reading of 35,800 feet, nearly 7 miles below the surface, confirmed the sonar findings. Squeezed inside their bubble of breathable air, the two explorers were closer to the Earth's center than man had ever been.
We took a self-portrait. That's the picture that you see. Said we're going to do it, and we did it.
But there was work to be done. Walsh and Piccard wanted to make detailed observations of the enormous trench. Unfortunately, the Trieste stirred up a cloud of fine, powdery sediment from the sea floor that obscured their view.
It's like being in a bowl of milk at that point. So, realizing we weren't going to see anything, we decided to go on back up to the surface.
Off the island of Guam, the Trieste surfaces after a descent into the Marianas Trench.
After 9 grueling hours underwater, Walsh and Piccard returned to the surface on January 23rd, 1960, and officially entered the record books for the deepest dive of all time. To this day, their extraordinary feat has never been repeated. The mission was a success, but the mystery remained. Geologists still didn't understand what could have formed the immense trench. And if they couldn't find the answer inside the trench, they would have to look elsewhere. Perhaps there was something somewhere on the ocean floor that might explain the trench's origins. Throughout the 50s and 60s, a team of geologists led by Princeton's Harry Hess compiled sonar data from all of the world's oceans. It was as though they had pulled out a giant plug to drain away all the water and expose the ocean floor. Their maps revealed that the Marianas Trench is just a tiny fraction of a network of enormous underwater canyons stretching right around the planet. But that wasn't all. Running parallel to the trench, on the other side of the Pacific, the map showed a giant underwater mountain range, the East Pacific Ridge. And this too is part of a global network, a 40,000-mile-long chain of mountain ranges that ring the globe like the seams of a baseball to make the largest geological feature on Earth. It was a major development in the investigation, one that scientists hoped might explain the trench's formation. The next step was clear. Investigators needed to understand whether there was a connection between the trench and the East Pacific Ridge. The breakthrough came from the unlikeliest of sources. During the Cold War, the U.S. built a vast network of underground seismometers to pick up atomic bomb testing around the world. Inadvertently, the seismometers also detected naturally occurring earthquakes. When geologists plotted these on a map, a pattern emerged. The earthquakes were clustered along the ocean's ridges and trenches. It was a discovery that transformed our understanding of the Earth. Geologists realized the friction that causes earthquakes comes from movements that must be occurring deep beneath the ridges and trenches.
With this great investment in seismology, it became possible to locate very precisely where earthquakes had occurred. And it was these things, the precise location, the depth, and the motion, that really gave the outlines of plate tectonics.
It was the birth of an extraordinary new theory. The solid layer of rock, the crust on which the land and ocean sits, is broken up into a series of vast slabs that geologists call tectonic plates. It's these plates that are moving, grinding past each other, and triggering earthquakes. The underwater ridges and trenches sit on the boundaries between tectonic plates. The East Pacific Ridge and the Marianas Trench lie on opposite edges of the Pacific Plate. The journey to discover what formed the Marianas Trench is accumulating additional evidence. The Trieste dived to the bottom of the trench and confirmed that it is the deepest point on the planet. Sonar maps then revealed the East Pacific Ocean ridge running parallel to the trench. To solve the mystery of the Marianas Trench, investigators needed to find out exactly what was happening at the East Pacific Ridge, and that meant exploring these vast mountains, 8,000 feet underwater. The pieces of the Marianas Trench puzzle are falling into place with the knowledge that it lies on the western edge of the Pacific tectonic plate. On the opposite side of the plate lies the East Pacific Ocean Ridge, part of an enormous chain of underwater mountain ranges that ring the globe to create the largest geological feature on Earth. Scientists had a hunch that this colossal ridge might help explain how the trench was formed. And they found a major clue halfway around the globe, where the ridge passed beneath the middle of the Atlantic Ocean. During the Cold War, the U.S. Navy developed a new technique to spot Soviet submarines. They scanned the seas with a tool called MAD, a magnetic anomaly detector, which could pinpoint steel hulls lurking in the deep. But they stumbled across something else. Running parallel on either side of the ridge, they found strange stripes of magnetic rocks, alternating positive and negative away from the ridge's peak.
Here's the mid-Atlantic ridge coming down through here. Almost perfectly symmetric on either side of that are these white and black stripes. These have often been called zebra stripes.
Geologists know that the Earth is like a giant magnet with a north and a south pole. But the magnetic poles aren't fixed. Every 300,000 years or so, the magnetic field suddenly flips 180 degrees. When the field flips, a compass that was previously pointing north will swing to the south.
This reversing of the Earth's magnetic field is a very interesting and exciting but very puzzling phenomenon for geophysicists to explain.
Scientists think this reversal explains the stripes either side of the ocean ridge. In the 1960s, geologists discovered that molten volcanic rock, known as magma, swelled up from deep underground to create the ridges in the Atlantic and Pacific. As magma wells up between the tectonic plates, it pushes the seafloor up and forms the colossal mid-ocean ridge thousands of feet high. When the rock is hot and molten, its magnetic minerals line up with the north-south direction of the Earth's magnetic field. As the magma cools, the minerals are locked in position. These rocks act as a permanent record of the magnetic pole's location when the rocks were formed. As more and more magma is forced up, the old crust is pushed away from the ridge and records the reversals in the Earth's magnetic polarity.
If you have reversals of magnetic polarity, then the seafloor acts sort of like a tape recorder and records these changes in magnetization. Then the pattern of magnetic stripes allows people to calculate the speed at which the plates are moving apart.
The zebra stripes are proof that over time, the seafloor in both the Atlantic and the Pacific is spreading away from the ridges at a rate of more than 2 inches a year. But geologists needed proof that magma created the ridge. If red-hot molten rock is forming the enormous mountain range in the Pacific, the surrounding water should be warm. In 1977, a team of scientists set out to discover whether this warm water really existed. Dudley Foster was the pilot for these historic dives.
It's been an exciting occupation because you're on the cutting edge of science. New discoveries all the time. Every cruise, there's a new group of scientists with new scientific objectives, and there's the exploration and the discovery. And that's really what puts the thrill in the job.
For weeks, the crew scanned the undersea mountains without success. And then they hit the jackpot. A bizarre pillar of rock, spewing hot, toxic gas.
And we saw the water was sort of shimmering, sort of like bubbling in a glass teapot or something. We stuck the temperature probe in there and measured 38, 39 degrees Fahrenheit, which was really amazing because the ocean's a huge heat sink. So to see something warm like that was kind of startling.
In these pillars of rock, the expedition had found the heat from the magma surging up from deep inside the Earth. It wasn't warming the water evenly along the ridge. It was channeled up through strange hydrothermal vents.
When you make these discoveries, you don't know how significant they are. The true significance of them maybe takes several years to appreciate. And this was one of those times.
For the investigation into the Marianas Trench, these vents are a decisive piece of evidence. They confirm that magma is continually creating new crust at the Pacific Ocean ridge. And magnetic zebra stripes prove that old crust is pushed away from the ridge towards the other side of the Pacific Plate, towards the Marianas Trench. But this presents scientists with a puzzle. If new crust is being created at the ocean ridge and the Earth isn't expanding, then the old crust must be disappearing somewhere else.
The reason that there's not getting bigger with seafloor spreading is because the same amount of seafloor is being destroyed in the Pacific.
Something in the Pacific Ocean is devouring the seafloor, and all the evidence points to the Marianas Trench. In the hunt to discover what formed the Marianas Trench, scientists now know crust created at the ocean ridge is being devoured somewhere and by something in the Pacific Ocean. They suspect the Marianas Trench is involved. But the proof would come not from the trench, but from these. The Mariana Islands, a chain of volcanoes that break through the ocean's surface 200 miles west of the trench. Scientists noticed the island chain mirrors the trench's exact shape. This led them to think the trench was responsible for the island's creation.
If you see pictures of the Marianas Trench, it's curved, and the line of volcanoes that it generates is curved exactly parallel to it.
Geologists believe that the trench formed the volcanoes via a process called subduction. Subduction occurs where two tectonic plates collide. As they grind past each other, the heavier plate is pushed beneath the lighter plate. The descending plate is forced down into the Earth's intensely hot interior called the mantle. It takes with it water and sediment built up over millions of years.
Volcanoes form above subduction zones not because the Earth is hotter there, but because this is where we're taking the water that once was in the ocean. It's taken into the mantle and gets sweated out, causes the mantle to melt, and this magma is what then rises and erupts explosively out these volcanoes.
The water in the sediment forces magma to swirl up and push through the plate above. And when it breaks the surface, it creates volcanoes, like the volcanoes that form the Mariana Islands. It was subduction that formed the islands west of the trench and gave investigators the breakthrough they'd been looking for. Because here, at last, was a process powerful enough to create the Marianas Trench. As the descending plate dives down, it digs into the mantle. Here, the colliding plates form a trench, a giant crease in the ocean floor. It seemed that scientists had finally explained how the trench was formed. There was just one problem. A very large problem. Around the world, subduction zones cause violent earthquakes and catastrophic tsunamis.
We know subduction is happening because of the active earthquakes, and these are the most devastating earthquakes. This is the earthquake that generated the tsunami in Sumatra. Also, the other very large earthquakes in Alaska and Chile.
But the Marianas Trench, the deepest subduction zone in the world, hasn't caused a devastating earthquake since records began in the 17th century. Investigators needed to know why.
That's the $60,000 question.
They hoped the trench's shallower western edge might provide the answer. Here they found an intriguing chain of underwater hills 2 miles below the surface of the sea. Engineers drilled down into the hills and collected core samples. And when the scientists analyzed the samples, they discovered the hills were actually volcanoes. And they spewed out not lava, but mud. The fine powdery mud is made up of a soft type of rock that has been ground up in the subduction zone. It seemed this soft rock might explain why there have been no major earthquakes at the Marianas Trench.
Everybody has a sense of what a volcano is, but not all volcanoes erupt igneous rocks. There's some volcanoes that erupt mud, and a certain kind of unusual kind of mud in the Marianas is made out of serpentine. And serpentine is a very weak rock, and it can be scratched with a knife or something like that.
Investigators realized the grinding plates crush the soft rock to form a lubricating mud that prevents large earthquakes. Then the mud bubbles up to the ocean floor, where it forms the strange mud volcanoes found along the trench's western edge.
Other parts of the world, like the Andes or maybe Indonesia, you've got two plates that are grinding together, and one of the plates is quite strong. And it takes a big earthquake to rupture that plate interface. But if these rocks are weak, like they are in the Marianas, where you've got these serpentinites, those are very weak, and it doesn't take much energy at all to get the two plates to glide one past the other.
At last, geologists had discovered what created the Marianas Trench. 50 million years ago, the Pacific Plate slipped under the edge of the Philippine Plate. As it bent and dived into the Earth's mantle, it formed the colossal Marianas Trench. And the plate is still moving. Like a giant conveyor belt, the Earth's crust travels slowly across the Pacific Plate, from its birthplace in the East Pacific Ridge to its graveyard 10,000 miles away in the Marianas Trench. Today, the Pacific Plate's movement can be tracked in real time.
Confirmation has come from GPS technology, where we can actually put a transmitter on an island and come back year after year and actually follow it moving a few centimeters a year towards the trench.
It's devouring the crust at a rate of 3 inches a year, about as fast as a human fingernail grows. Every 4 million years, it swallows an area the size of the United States. By consuming the crust created at the Pacific Ocean Ridge, the ravenous Marianas Trench is the world's largest recycling plant. But there was one remaining and major piece of the puzzle to find. Scientists still didn't know why it is the deepest trench on Earth. They suspected the age of the seafloor at the bottom of the trench may provide the answer.
It turns out there's a really strong relationship between the age of the seafloor and its depth in the water.
In 1999, a team of deep sea drillers returned to the trench to collect core samples.
One great thing about drilling this ocean crust is we actually got pieces of it. So we're holding in our hands here the material that's actually getting subducted at the Marianas Trench, and it turned out to be 170 million years old. So we can say with confidence that's the oldest ocean floor before it's getting swallowed up in the mantle at the trench.
But why is this piece of rock the oldest on the ocean floor?
The seafloor at the Marianas Trench is so old because it's been so long since it was born. So it was born in the equivalent of the Eastern Pacific today, and it's just been going on longer than any other place in the oceans before it's been subducted.
The Pacific Plate is the planet's largest tectonic plate, covering an area 11 times the size of the United States. When crust bubbled up at the ridge 170 million years ago, It was light and buoyant. But as it traveled 10,000 miles across the plate, it cooled and became compact and dense. Over millions of years, the dense crust got heavier and began to sink into the mantle below. Scientists realized that because the crust at the Marianas Trench is the oldest ocean crust, it's also the heaviest, and so has sunk deeper into the mantle than any other area of ocean crust. Here at last was the explanation for the trench's extraordinary depth. The picture of the Marianas Trench is almost complete. The investigation into the Marianas Trench has one final puzzle to solve. At the trench's southern end, the sea floor plummets a further 10,000 feet into a 7-mile deep chasm called the Challenger Deep. It's the lowest point on the planet. But so far, scientists have been unable to explain why this one section of the trench is so deep. Now, they believe the shape of the descending tectonic plate may hold the answer.
The Challenger Deep, in addition, is a little bit deeper because of some peculiarities relating to how the slab that's going down is behaving.
A narrow slab of crust has torn away from the Pacific Plate's descending edge.
Well, it's basically got to do with how the slab pushes the mantle out of the way. Where you have a narrow slab, like you have at the Challenger Deep, it can sink almost vertically because the mantle that it's trying to displace can move around out of the way.
Investigators have finally unraveled the mysteries of the Marianas Trench. And in the process, they've made a discovery with implications that stretch far beyond the trench itself. Studying the ocean ridges led geologists to believe that magma welling up at the ridges was pushing the plates apart. But the exploration of the Marianas Trench has changed this idea forever.
People used to think that maybe the magma would kind of push the plates apart. And that idea is largely discounted now.
As the ocean crust travels from the Pacific Ocean ridge to the trench, it changes from a buoyant, red-hot magma into a colder, denser, and heavier crust. The plate's leading edge becomes so heavy that it drags the rest of the plate along behind it.
The heavy, cold plates of the trenches are sinking down into the mantle and pulling the plates apart at the ridges, and the magma just passively fills in the gaps.
The investigation into the Marianas Trench has revolutionized our understanding of how the Earth's plates move. We now know a worldwide network of subduction zones drag tectonic plates around the globe, powering the movement of continents over millions of years, and moving the very Earth we stand on.
The plates that are moving fastest on the Earth are the ones that have all the trenches.
The Pacific Plate is the fastest moving of the 9 major plates on the planet because it is surrounded by dozens of destructive trenches like the Marianas. They are consuming the ocean crust faster than the ocean ridge can produce it. Over millions of years, the Pacific Plate will shrink until sometime in the distant future, the largest ocean on Earth will disappear. Australia will crash into the United States, reshaping our planet. Perhaps one day, downtown Seattle will compete for real estate with a suburb of Sydney, Australia. And all because of subduction zones like the Marianas Trench. By But for all its significance, man has only ever dived to the bottom of the trench once, and there are no immediate plans to return.
Imagine asking someone, what is the flora and fauna of California? And saying that someone spent 10 minutes there, picked up 2 ants, come back, and said they sampled California. That's probably how well we know the Marianas Trench.
To date, less than 5% of the world's oceans have been explored. But only by returning to the ocean's very deepest reaches will we fully comprehend the incredible forces that recycle and rebuild our world.
The way I like to think of it is that ocean exploration leads to new research questions. And if we don't have exploration, we don't even know the right questions to ask.
It is now known what a geological wonder the Marianas Trench is. Since this deep chasm in the Earth's crust was first discovered with a length of rope and a lump of lead more than a century ago, evidence has piled up. A record-breaking dive to the lowest point on Earth. Giant undersea mountain ranges with bizarre magnetic zebra stripes. Proof that the ocean crust is spreading towards the hungry Marianas Trench, lined with slippery mud volcanoes which prevent devastating earthquakes. And the planet's oldest ocean crust, the reason that the Marianas Trench is the deepest point in the oceans. In the darkest and most remote place in the world, scientists have added to their knowledge about the powerful forces that contribute to the dynamic story of our planet. Earth, a 4.5 billion year old planet, still evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede, the Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, Krakatoa, one of the deadliest volcanoes in the world. More than 100 years ago, it erupted with such devastating fury that it wiped itself off the face of the Earth. In the process, it sent out the loudest sound in recorded history and killed more than 36,000 people. And now, this deadly volcanic beast is back. Geologists investigate one of the world's fastest growing volcanoes to hunt for clues that will tell them if and when Krakatoa will explode once again with the same cataclysmic force. As they prise apart the rocks, the answers they find will be another piece of the puzzle of how the Earth was made. Krakatoa is one of the most dangerous volcanoes the world has ever seen. When it exploded apart in 1883, the blast was heard over nearly 10% of the Earth's surface. It was a worldwide clarion call announcing the awesome power of volcanoes. The site of this monstrous eruption lies between the Indonesian islands of Java and Sumatra, in a channel known as the Sunda Straits. Today, a new volcano has staked its claim in exactly the same spot. It's called Anak Krakatau, meaning the child of Krakatoa. Right now, it's in the middle of a new and extremely dangerous phase. Dr. Charles Mandeville traveled here to see if the child will one day be as deadly as its parent, to see if history is about to repeat itself. the stakes are high. At risk now are the 1 million people of Java and Sumatra who live within 50 miles of the volcano.
Oh wow, look at that. We got a little explosion going on. I've kind of been following this from the internet from my office, but it's actually good to kind of see the thing live again. I've noticed in coming here that the volcano itself has grown possibly as much as 250 to 300 feet since the last time I've actually stood on its crater back in 1990.
Growing at a rate of 12 feet a year, the 1,033-foot volcano is both one of the fastest growing and youngest volcanoes on the planet. This remarkable footage shows its explosive birth in June 1927, when it first broke through the seafloor and erupted out of the water. Its rapid growth is clear evidence that this new volcano is extremely active. But will it be as deadly as its parent? These eruptions are always accompanied by a series of ground-shaking tremors. For geologists, these small earthquakes are evidence that this volcano is entering a more destructive phase. Seismographs have been buried deep on Anak slopes to record this underground activity. But these small quakes are not the only sign of a dangerously active volcano. A more subtle clue is right beneath Mandeville's feet.
Black sand beaches are very common in volcanic areas. The minerals and the glass fragments that comprise the ash that the volcano erupts is typically dark charcoal gray colored, and usually these materials don't stand up to weathering over long protracted periods of geologic time, but you find them in relatively fresh, pristine form when you're near an active volcano.
Anak Krakatau is rarely completely quiet. But the level of activity in 2008 shows that the volcano has become unusually violent. To discover just how much of a threat it could pose in the near future, volcano detectives must turn to their history books to learn what made its parent, Krakatoa, so destructive. This is a story that has fascinated geologists for over a century.
What got me switched onto volcanology was the 1883 eruption. I learned about this at school, and I remember thinking how incredible that an island could just blow itself into oblivion. You know, what was going on? What was that all about? What was special? You know, how does that happen? And could it happen again elsewhere on Earth?
Before it exploded in 1883, Krakatoa was an uninhabited island with 3 jagged peaks, covered in lush vegetation. It was part of the Dutch East Indies, a thriving, bustling hub of international trade. Indonesia's wealth of minerals and spices attracted many Western traders, journalists, and geologists. Their reports provide first-hand accounts of what happened before and during Krakatoa's deadly and shocking eruption. There had been no hint of volcanic activity in anyone's memory. No one had a clue that Krakatoa was about to blow. Beneath its green and placid surface, Krakatoa was a time bomb waiting to explode.
So the first idea the locals would have got that anything strange was happening on their island would have been in May 1883. The earthquakes, earth tremors.
These tremors reached as far as the capital, Batavia, more than 100 miles away. Few suspected that the island of Krakatoa, seen on the distant horizon, was to blame, and that these earthquakes were the first clue to its deadly potential. Then, on May 20th, 1883, Krakatoa announced that it was no mere island. one of Krakatoa's 3 peaks exploded with extreme force, shooting a plume of ash hundreds of feet into the air. But after these initial fireworks, the activity appeared to cease. The local population breathed a sigh of relief. Thinking it safe, the governor of the Dutch East Indies sent a research party of geologists to the island in late May, where they observed the scorched landscape and smoking crater with amazement. Their meticulous report gives modern-day geologists the first clue as to what lay behind Krakatoa's immense power. A key discovery was a layer of pumice 1 foot deep that covered the island's shores. This pumice is the solidified lava that comes from the heart of a volcano, and it's riddled with bubbles. These bubbles suggest to geologists that Krakatoa is a stratovolcano.
And those volcanoes tend to be the classic volcanoes that you see in textbooks. They're very steep-sided, like sort of sharp, almost triangular-type mountains.
These are the most dangerous types of volcanoes on Earth. They are fueled by molten rock called lava, known as magma when it's underground. The magma that flows through these volcanoes is like liquid dynamite.
Stratovolcanoes are dangerous because of the source of lava that they erupt. And the lava that comes out of stratovolcanoes is very sticky, viscous lava. And the danger there is that the sticky lava often contains large amounts of gas.
The bubbles inside the pumice discovered on Krakatoa in 1883 show that the magma was once packed with explosive gases. Because the magma was so sticky, a term describing its thickness and resistance to flow, the gas could not easily escape.
And the formation of gas bubbles in the sticky lava can be powerful enough to actually rip the lava apart, and in the process you actually tear away the volcano. The whole thing becomes explosive, and you produce very dangerous volcanic activity.
Krakatoa's magma had another deadly property.
In some situations, the lava can become so sticky that it sort of freezes up and congests or chokes up the volcano. It forms a kind of a plug or a seal. And what will happen is that over time, more magma is coming up and being trapped beneath that plug. At some time in the future, the pressure would be so great that there'd be so much magma wanting to get up that you would just rip the plug apart, and that can produce, again, a catastrophic volcanic eruption.
This is exactly what happened at Krakatoa on May 20th, 1883.
From then onwards, over the summer, it quietened down a bit, but this was really the kind of calm before the storm.
The investigation into Krakatoa's deadly potential has produced important evidence. The frequent earthquakes on Anak Krakatau today indicate the volcano is still dangerous. The pumice from 1883 reveals that Krakatoa was a stratovolcano, its sticky, gas-rich lava making it dangerously explosive. Krakatoa's eruption in May 1883 was spectacular, but beneath the surface, Krakatoa was refueling. An even greater eruption was gathering force out of sight and out of mind. Anak Krakatau is one of the fastest-growing volcanoes in the world. Geologists are investigating its threat to the region. They have turned to the past to uncover what made its parents so deadly. In 1883, exactly 100 days after Krakatoa first blew, the volcano showed its true power. This final phase of eruptions began at 6 minutes past 1 on the afternoon of August 26th. All three volcanic peaks erupted simultaneously, hurling dense clouds of ash and smoke an astonishing 17 miles into the sky.
The eruption of Krakatoa was one of the biggest volcanic events of the last few hundred years, and it would have been, to people observing it, it would have been like the beginning of the end of the world, if you like.
The power of this eruption was immense, like a giant jet engine aimed skywards. The air quickly became choked with tons of thick black ash, blotting out the sun.
So temperature, because of all the ash in the atmosphere, would be stifling, and if you were very near on the, for example, the west coast of Java, you'd be getting the ash in your throat and in your eyes. It would have been a real vision of hell.
And a nightmare that showed no signs of ending. By the next morning of August 27, 1883, Krakatoa's 3 craters had been raging for more than 14 hours. Then, sometime between 5:30 and 10:02 a.m., the land was deafened by a series of 4 huge explosions. The noise was so loud it could be heard over 2,000 miles away in the Australian desert near Perth. The third was the loudest recorded noise in history, the equivalent to 200 megatons of TNT, 13,000 times the size of the bomb that destroyed Hiroshima. What created this awesome explosion? The hunt for answers takes geologist Charles Mandeville to the jagged island of Rakata. This tiny island is in fact a part of the once mighty Krakatoa.
The record of what the volcano did from May 20th to August 26th to 27th is here, represented on the island by the layered deposits that we see preserved in the jungle. This is a gold mine for a volcanologist trying to reconstruct the events that took place here, because each one of these deposits tells us something particular about what the volcano was doing.
This pumice was thrown out of the heart of the volcano in 1883. Mandeville believes that it holds the key to understanding the forces that destroyed Krakatoa.
What I have in my hand is a mixed pumice or streaked pumice, and what it represents is that we had 2 magmas mingling in the conduit of the 1883 eruption of Krakatoa.
The stripes are proof of the 2 types of magma inside Krakatoa. The lighter band represents the cooler, gas-rich magma that was present during the earlier eruption in May. This eruption only partially emptied the magma chamber. By August, this void was filled from deep below by searingly hot, dark-colored magma. When these 2 magmas mixed together, it was a lethal cocktail. The intense heat of the dark magma caused the huge amounts of gas within the light magma to expand.
The magma chamber that was holding this mixed bag became overpressurized to the point where it exceeded the rock strength of the roof rocks above it. And when that happens, you can get really rapid ascent of magma to the surface.
When this magma exploded from the surface, it ripped apart tons of rocks with an ear-splitting blast. This mega explosion caused the loudest noise in recorded history. The striped pumice on Rakata proves that magma mixing was the trigger. But Krakatoa wasn't just the loudest volcano in history. It was a killer. Because Krakatoa itself was uninhabited, some of the volcano's first victims were at Ketimbang, a village on the southern coast of Sumatra. But Ketimbang is on the mainland, 20 miles from Krakatoa, and separated by the waters of the Sunda Straits. How these people fell victim to the deadly ashes was a mystery. To uncover the answers, we have to return to the scene of the crime, Rakata, and to these imposing white cliffs. They may seem part of an ancient landscape, but these 200-foot white cliffs were laid down in a matter of hours. They are what's left of a raging torrent of hot gas and rocks, a terrifying force of nature known as a pyroclastic flow.
Pyroclastic flows travel extremely quickly, so you can't outrun them. They're also extremely hot, several hundred degrees centigrade, so they will, if you're caught in the middle of one, they will incinerate you instantly.
Perhaps the most famous victims of a pyroclastic flow lie at Pompeii, the Roman settlement that was utterly destroyed during the eruption of Vesuvius in Italy in the year 79. The perfectly preserved remains of the people here are testament to the power of these fiery avalanches.
And most people die not because of 100% burns, but because they inhale the gases, which are so hot that they just destroy the air passage in the lungs instantly. And so after 2 breaths, they're dead.
The sheer size of the cliffs at Rakata have led geologists to estimate that the pyroclastic flows thrown out by Krakatoa were an amazing 2,800 feet high. But the victims of this deadly torrent were on the other side of the Sunda Straits. What happened next was truly astonishing.
Pyroclastic flows are ground hugging. In other words, they follow the ground surface as they go down. But they also have an upper part which is very rich in gas, so it's low density. Now, when the pyroclastic flow hits the sea, the dense bit carries on down onto the ocean bed, but the gas rich, but still very hot bit, goes hurtling across, scooting across the top of the water. There's virtually no friction between the gas and the water, so it can travel a very long distance.
Over 2,000 people at Ketimbang perished from the burning debris that could not just walk on water, but run at amazing speeds of up to 200 miles per hour across 20 miles of open sea. The investigation into the Krakatoa volcano has pinpointed the extraordinary force that ripped the island apart. Striped pumice is proof that magma mixing created the vast explosion. 200-foot cliffs on the island of Rakata are evidence of vast pyroclastic flows, big enough to cross the ocean and claim the volcano's first victims. But contemporary reports show that most of Krakatoa's victims were not killed by these deadly avalanches, but by a very different force of nature. August 1883, Krakatoa's second and most deadly eruption. More than 2,000 people were killed by searingly hot pyroclastic flows. But there was worse to come. These gigantic boulders are on the shore of Anyer in Java, 22 miles away from Krakatoa. They are a crucial clue to what the volcano did here, and a stark reminder of what could one day happen again. They are made of coral, which can only grow underwater. So some immense force unleashed by Krakatoa must have put them here. These shattered bricks are another piece of the same puzzle. They are all that remain of a lighthouse that once was one of the sturdiest buildings on the Java coastline, but no match for Krakatoa.
I'm standing at the top of the new lighthouse in Anyer, 120 feet above sea level, built 2 years after the eruption of Krakatoa in 1883. The old lighthouse down there is nothing but a trace of bricks because it was wiped out by a large tsunami.
Eyewitness accounts detail the exact height of this terrifying wave.
Difficult though it might be to comprehend, the momentum of that wave would have taken the water up to the level that I'm now standing.
Krakatoa's death throes had triggered a massive wall of water that now raced towards the shore at Anyer.
I don't think anyone living along the shores of Western Java or Southern Sumatra would have known about the tsunami that they were about to face, and certainly nobody would have been able to survive those sorts of wave heights.
The power of the wave can be seen in this 600-ton block of coral that was ripped from the seabed and smashed the lighthouse to pieces. Still here today, It provides some of the clearest evidence of the immense power of Krakatoa's 1883 eruption. The same wave that shifted this boulder also destroyed houses, villages, and transport, leaving nothing but twisted wreckage behind. The mighty wave even picked up and stranded a Dutch steamer, the Beirut, 2 miles inland. This immense tsunami claimed the lives of more than 34,000 people.
It's quite possible that those people who lived in the villages in western Java and southern Sumatra thought, well, the volcano's out there somewhere, it's an island, so it can't possibly affect us here. But of course, the eruption itself triggered the tsunami, which meant that the water adjacent to the volcano was being displaced right across to where they lived. So, you know, that feeling of safety was sadly misplaced.
For modern-day investigators, the puzzle was how fire and water had combined to wipe out an entire region. The evidence came from the shattered remains of the volcano itself, Rakata Island, part of one of Krakatoa's 3 original peaks. Its sheer vertical cliff face tells volcano detectives about Krakatoa's final moments.
When you have a very large volcanic eruption, you evacuate a lot of magma. It leaves behind effectively a hole, so quite often the crust just collapses down into that hole, and that leaves behind what we call a caldera.
Krakatoa had ejected such vast amounts of burning magma and rock, it could no longer support itself. Drain away the water, and we can see how it collapsed, creating an immense caldera.
So this cliff behind me marks the edge of the 1883 caldera. Under the boat, this water depth is about 40 times as deep as most of the area around us. The scale of this collapse is pretty big. It formed a caldera that's about 3 miles in the north-south direction by about 5 miles in the east-west direction.
This immense collapse has only occurred once in recorded human history. The combined weight and power of Krakatoa's awesome pyroclastic flows and this huge collapse was more than enough to trigger the tsunami. The riddle of just what had caused Krakatoa's tremendous tsunamis had finally been solved. When the smoke had cleared and the waters receded from the most devastating eruption in recorded history, the island of Krakatoa had vanished. In total, Krakatoa had killed 36,417 men, women, and children. It was, without doubt, one of the most dangerous volcanoes in history. But while investigating the 1883 eruption, scientists discovered ancient lava flows hidden in the jungle and on the seabed. This deadly volcano had struck before. But when scientists dated the lava flows, they hit a problem. Radiocarbon dating was only able to place the eruption to between the 1st and 13th centuries, a spread of 1,200 years. Scientists needed more information in order to try and shed light on a new Krakatoa threat and help the hundreds of thousands of people living in the area. The trail of evidence at Krakatoa had gone cold, literally. Because thousands of miles away from the sweltering heat of Indonesia, in the frozen wastes of the Antarctic, scientists recently discovered a critical clue to Krakatoa's explosive past.
Well, ice cores are cylinders of ice that we drill from the ice caps in Greenland and Antarctica. If you look at things like volcanoes, any material coming from the surrounding oceans make its way to Antarctica, where we can detect it in the ice. You might imagine that we see the dust and the ash from a volcano. In fact, very little of that from the big Indonesian-type volcanoes ever makes it to Antarctica. So what we do see is sulfuric acid. Big volcanoes, it spew out a lot of sulfur dioxide into the atmosphere, which is oxidized into the sulfuric acid, which we then measure in the ice.
The sulfuric acid cannot be seen in the ice cores with the naked eye, but can only be detected back at the British Antarctic Survey's lab, where the cores are kept at a continuous minus 13 degrees Fahrenheit.
So this is a piece of core from Antarctica. This is a piece from James Ross Island. It's about 10,000 years old, this ice. What we're doing now is measuring the volcanic signals. And what we see is very, very distinct, clear electrical pulses that come from the sulfuric acid from the volcanoes. So very quickly we can see all the volcanic signals throughout the whole core.
One of the strongest signals found in the ice cores is from the 1883 eruption of Krakatoa.
What we can see from the 1883 eruption, we can't see the ash, but we can see a very large peak in sulfuric acid. In fact, it's one of the biggest peaks we've got in the last 1,000 years. It's such a big peak, in fact, that we use it to date the ice cores because it's like a reference horizon we can see there.
Each ice core is like a diary of the Earth's climate. Each layer of ice represents 1 year. In the same way that we can count tree rings, scientists can count back each layer of ice to determine the exact date of any eruption. Counting back from the 1883 signal, there is a huge spike in the sulfuric acid levels in the year 535. This is clear evidence of an enormous eruption during the dying days of the Roman Empire, an eruption far greater than Krakatoa's in 1883.
We are now beginning to come to the conclusion that yes, there was a large volcanic eruption in 535. In fact, it looks one of the biggest ones on the record in terms of how much sulfuric acid it put into the atmosphere.
The ice cores tell us a lot about this mystery volcano. Its eruption was so enormous that its impact was global. Its date falls exactly in the middle of the time span of the lava flows around Rakata. Could it be Krakatoa? The clues seem to fit. If they are the same eruption, this is evidence that Krakatoa has a far more deadly past. And potentially a far more deadly future.
Can we tell whether it's come from Krakatoa? And that's more difficult. We can see it in Antarctica and we can see it in Greenland, so that tells us it was probably somewhere mid-latitude, so somewhere round about the equator maybe. So it's a possibility, but we cannot really pin it down at the moment.
Despite this uncertainty, there is no doubt of Krakatoa's capacity for destruction. The steep cliffs at Rakata show that Krakatoa collapsed to form an enormous caldera, triggering a deadly tsunami. And yet ice cores from Antarctica suggest that Krakatoa may have exploded before, with even more force than 1883. To discover what originally created not only 1883 Krakatoa, but also the current Anak Krakatau, scientists will have to travel even further back in time, some 2 million years. The source of Krakatoa's awesome power remained a mystery to scientists for centuries. One clue is its location. Indonesia contains more volcanoes than anywhere else on Earth.
Indonesia is a jackpot for volcanologists, simply because the evidence of volcanic centers that may have lasted several million years are available and ready for observation and study.
Incredibly, there are 21 of these fire mountains on the island of Java alone, an area the same size as New York State. The National Park of Tengah Bromo in East Java is one of Indonesia's most active volcanic zones.
To view a landscape like this is actually humbling, because it tells us that there are forces at work that far exceed anything that mankind can construct.
But why there should be so many volcanoes in such a small area, no one could explain. A key discovery was that Indonesia lies adjacent to the notorious Ring of Fire, a chain of volcanoes stretching around the entire Pacific Ocean. In the 1950s, American geologist Harry Hess began research into the groundbreaking hypothesis known as seafloor spreading. This laid the foundation for plate tectonics. Plate tectonics is based on the idea that our planet is not a perfect and unbroken sphere. It's composed of 8 major tectonic plates that jostle and jar against one another. These plates are driven by heat from the planet's core. Here in Indonesia, the plates collide faster than almost anywhere else on Earth. The volcanoes here are created when the heavier oceanic plate is pushed under the lighter continental rock. This is subduction. When the rock is pushed deeper, it melts to produce magma. Over thousands of years, it builds up into a vast magma chamber many miles beneath the surface of the Earth. Eventually, the pressure of the extra magma becomes too great for the Earth's crust. The magma forces its way up to the surface in a storm of hot ash and boiling lava. A volcano is born. In the case of Indonesia, this is a nation constructed almost entirely from volcanoes.
Most of Indonesia is in fact composed of volcanoes that initiated from somewhere down below sea level, rose up to sea level, and then grew as islands and amalgamated to form bigger land masses that now comprise the Indonesian nation.
Using the theory of plate tectonics, scientists can rewind the clock. 45 million years ago, the Australian plate started to move north rapidly. The island chain of Indonesia began to emerge from the ocean at the point where the two plates collided. Vast numbers of volcanoes exploded as the Australian plate was pushed deep into the bowels of the Earth. Krakatoa was a product of these same forces. And it was 2 million years ago, as our early human ancestors were taking their first tentative steps, that the volcano was created.
So the fact that under the Sunda Straits of Indonesia you have all these processes taking place 70 and 80 miles down below the surface made it inevitable that a volcano like Krakatoa came into existence, but also had a catastrophic eruption.
What made Krakatoa so much more dangerous than hundreds of other volcanoes in Indonesia only became clear in 1988. Scientists discovered that large clusters of earthquakes were taking place beneath the Sunda Straits. Earthquakes are common along plate boundaries, but this amount was off the charts. This major clue would enable scientists to finally identify the killer factor in Krakatoa. Beneath Krakatoa, in the middle of the Sunda Straits, the subduction zone contains a kink. This twists and rips the Earth's crust and provides even more material to fuel Krakatoa's hungry magma chamber.
Where you have those kinks, two things can happen. Firstly, there might be a greater chance of earthquakes because the kink itself actually starts to tear or rip. And secondly, where the kink is might generate more melting. And it's the melting that takes place in the mantle that ultimately leads to the lavas that erupted from the volcanoes at the surface.
Finally, the origins of Krakatoa had been revealed. Hundreds of volcanoes in Indonesia show that the country lies on a volatile plate boundary. Unusually high numbers of quakes show that Krakatoa lies on a deadly kink within this zone. But can scientists now use this knowledge to predict Krakatoa's future? A prediction that is today more important than ever, because the volcano is back, and it's getting bigger every day. Today, these shattered islands are all that remain of the cataclysmic 1883 Krakatoa eruption. But a deeper understanding of this event is now more important than ever, because out in the Straits, a new threat is growing. Krakatoa is back, in the form of Anak Krakatau, Indonesian for Child of Krakatoa. And that child is now an angry teenager. Like a phoenix from the ashes, Anak Krakatau is growing directly over the site of the original Krakatoa volcano, leading scientists to conclude it's being fed by the same magma chamber deep beneath the Sunda Straits. This deadly heritage means that Anak could potentially be one of the most dangerous volcanoes on Earth. But just how immediate is this threat? Since its explosive beginnings in 1927, Anak has erupted frequently and violently. As one of the fastest growing volcanoes on the planet, this 1,033-foot high mountain bears watching. Predicting exactly when another major eruption will happen is difficult, but there are clues. Underground tremors are a sure sign that the magma deep within the volcano is starting to move.
We have seismometers stationed on the volcano that tell us when rocks are breaking not just at the vent, but in the subsurface, heralding the arrival of new fresh magma into the edifice, into the cone.
These details are transmitted via radio signals to the monitoring station on the mainland, which is operated 24 hours a day. They have a simple scale to measure the threat, running from 1 to 5. Anything above a 3, and they go on red alert. At the moment, it's hovering around the danger zone, a level 3. The type of magma within the volcano is another way geologists can judge the potential of a major eruption. But the magma itself is impossible to test, as it lies several miles deep within the Earth. The next best clue is to look at what has been literally thrown out of the volcano. Lava bombs.
I've got my hand on a basaltic andesite scoria bomb that was probably blown out of a vent about 3/4 of a mile from here. And you can imagine to be hit by one of these would not be a good situation. These can actually range up to things that are the size of refrigerators and television sets, and they're thereby making them even more lethal, particularly when they're traveling at 120 miles an hour.
Mandeville analyzes these rocks made up of basaltic andesite, which will give him a clue to the makeup of the magma deep underground.
Part of what this composition tells me is the composition of magmas being erupted at Anak are unlike what was typically erupted at the 1883 eruption of Krakatoa, which was much more silica-rich and much lighter in color, typically light beige to almost white.
The more silica in the magma, the more viscous or sticky it is. And that's what contributed to Krakatoa's explosive eruption in 1883. The explosive gases were trapped in the magma, and pressure had been building up over time. Fortunately, the dark color of the lava bombs from Anak Krakatau are evidence that the magma is low in silica. And the explosive gases have yet to reach critical 1883 levels. But this is not a permanent state.
Over the years, a magma like this can, in fact, evolve into something that was that explosive.
As Anak Krakatau grows, the magma will certainly become thicker and stickier. As in its parent, once the magma gets too sticky, the vent could become blocked. The silence could signal disaster. It means that pressure could be building up inside. Too much pressure, and Indonesia could suffer another cataclysmic explosion. than 100 years of investigation into Krakatoa has helped unlock the secrets of its past and provided scientists with strong evidence that Anak Krakatau is following in its footsteps. The pumice from 1883 suggests that Krakatoa was a deadly stratovolcano. The stripes in the pumice show that the massive 1883 eruption was triggered by an injection of superhot magma. It was this that blew the volcano to pieces. The remains of vast pyroclastic flows that were over twice the height of the Empire State Building, plus the immense caldera, show the massive scale of Krakatoa's 1883 eruption. But most ominously of all, the position of Anak Krakatau near the deadly ring of fire directly above a kink in the subduction zone means that a future massive eruption is inevitable.
A lot of the Anak Krakatau activity that we now witness today is actually almost a continuation of the volcanic activity that took place back in 1883. We could have another eruption here on the scale of the 1883 eruption of Krakatoa.
The 1883 eruption of Krakatoa may be the most famous, but it is a geological certainty that it won't be the last. Krakatoa is on the rise again. Dynamic proof that the Earth is never at rest. Earth, a 4.5 billion year old planet, still evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede, the Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, the 450 million year old geological history of New York City is explored. A metropolis pockmarked with strange rocks, haunted by footprints of ancient giant reptiles, and lined with a vast curtain of solidified lava. Scientists investigate the evidence for fiery volcanoes, massive floods, and ice sheets 4 times as high as the Empire State Building. The clues to understanding New York City's geological past provides a window into the formation of the Earth itself. The investigation into New York City's geological history begins here, with Manhattan's rocky outcrops. These rocks are clues to how the land was made and how its geology helped it become a dense, thriving, pulsating city. They're scattered all over Manhattan, poking through the surface of parks and through the concrete between the buildings. Some, squashed between 2 apartment blocks, are the size of a whale. They are the extraordinary survivors of ancient times. Most importantly, they are the surface tips of the bedrock in which Manhattan's buildings are anchored. Gigantic skyscrapers stand in 2 clusters, in downtown and midtown. In the section between, the buildings are lower. The clues to the shape of Manhattan's familiar skyline are the rocks beneath the surface. A leading expert on the rocks in New York is geologist Charles McGarry.
The entire history of the development of the Earth's crust is emblazoned in the rocks beneath us. The rocks here in New York City harbor an ancestry that dates back over 1 billion years of time.
McGarrian is searching for evidence to show how the city's bedrock was made. At Inwood Hill Park in Upper Manhattan, he's found an extremely hard piece of the bedrock known as Manhattan schist. To the untrained eye, it's just a piece of rock. But to McGarrian,
This is his first clue.
The rocks that we're looking at right here are rocks of the Manhattan Schist Formation. And these rocks are very severely deformed. And the structures here in this rock is a structure that comes up like this, bends around, and comes back down on itself as such. And in three-dimensional view, it's a structure that looks something like this, a very, very tight fold with a plunge towards the south here. These are rocks that were very, very strongly deformed over protracted periods of time. And it's the same bedrock that occurs over much of New York City.
This tight fold in the rock suggests New York's bedrock was formed under great pressure. To confirm this hunch, Megarian takes a sample to the lab for detailed analysis. Radiometric dating proves this rock is about 450 million years old. But the rock has even greater secrets to tell. It contains a kaleidoscope of minerals, which opens a window into the ancient world.
To me, minerals are like the instrument cluster in your car. They tell you everything about how your car is running.
Megarian uses a microscope with polarized light to view the minerals.
The examination tells us the former depth regime, how deep the rocks were. They tell you the age of the rocks. They tell you everything you want to know about the development of the Earth's crust.
What's striking about these samples is that the minerals inside are elongated. It is a clue that these rocks must once have been crushed by massive forces. And the colors support this theory. Under the polarized light, the sample from Inwood Hill Park shows up blue. This comes from a mineral called kyanite, which forms at great depths. It's conclusive evidence that this rock was compressed deep under the surface. Rocks forged at these depths are much harder, ideal for a city's foundations. But what gigantic weight was on top? Megarian believes there is only one answer. The rock was once buried under the crushing weight of a chain of massive mountains.
The minerals that we find in the bedrock units of New York City tell us that the rocks of New York City were formerly buried when they were formed under very high pressures. And those high pressures indicate that these rocks formerly were produced at depths of 20 to 25 miles. And probably the mountains were as high as the Alps are today.
But even the most impressive mountain chains can't survive the ravages of time. The Rocky Mountains, for example. Millions of years ago, they soared nearly 6 miles into the sky. Today, erosion has halved their size. The same process happened in New York. Rain, wind, and ice wore the ancient mountains almost flat. But the microscopic crystals found in the rock in Manhattan testify that they existed in the past. How did the mountains form? The answer lies in the way the Earth's crust moves. A network of interlocking individual pieces makes up the Earth's surface. Geologists call them tectonic plates. Over millions of years, they collide and break apart to form different continents. 450 million years ago, the Earth's surface looked completely different. North America was much further to the south.
North America was tilted 90 degrees clockwise from its present orientation, and it was straddling the equator. As such, the climate was tropical. The east coast of North America was really experiencing Club Med conditions.
The weather may have been awesome, but the ancient East Coast was heading for trouble. The plate beneath it was moving. The East Coast was on a collision course with ancient West Africa. 450 million years ago, they collided. The impact unleashed geological chaos. Under intense compression, the land was forced upwards to form a soaring range of mountains.
The collision that took place is the most fundamental and impressive mountain building event to affect the east coast of North America.
Today, all that remains are their stumps. Stumps that form the bedrock of modern-day New York. The collision that built up the ancient mountains also folded the bedrock into dips and rises. These folds are responsible for the shape of Manhattan's skyline. The city boasts two clusters of skyscrapers in downtown and midtown. Here, the hard bedrock that formed deep underground was forced up. It is now close to the surface and provides solid anchorage for the high-rise buildings. In the dip in the middle, the rock was folded down. The area is filled with loose sediments, less suitable for skyscrapers.
When the bedrock is at the Earth's surface, where it's actually exposed, then it's pretty easy to build tall buildings because you can root them directly into solid rock. However, in areas where the bedrock is deep and covered by glacial sediment, in those cases, it's very difficult to build tall buildings because you need to root those buildings either into solid rock or build concrete abutments called caissons that can support tall buildings.
New York's deep history is beginning to take shape. Building up from tiny crystals in the rock, scientists revealed how New York's bedrock was formed under the crushing weight of a massive ancient mountain range. The result was hard Manhattan schist, a perfect foundation for the city's skyscrapers. But New York City still had a long way to go. The colliding plates created an enormous landmass, the last great supercontinent called Pangaea. New York was now trapped in the center. But somehow, it made it back to the coast. Hidden beyond the city's streets is evidence of huge volcanic eruptions, mass extinctions, and continents torn into pieces. Clues that could explain how New York became one of the world's great maritime cities. Investigators are piecing together how New York City's unique geology was formed. Much of its early success as a trade and commerce center is owed to its deep water harbor and its location at the coast. But 450 million years ago, things were different. The area of New York City was landlocked, embedded in the heart of a huge supercontinent. How did it get to the coast? The investigation fast forwards 250 million years. In a quarry in New Jersey, 25 miles northeast of Manhattan, paleontologist Paul Olson unearths the first of a string of clues that could explain how New York City reached the coast. A giant fossilized footprint.
This is the footprint, actually the mud that filled in the footprint, of a 4-footed crocodile relative that was the dominant carnivore during the late Triassic. You can see the toes here have little pads on them, and here's the handprint. And these animals would have been, in this case, about the size of a modest crocodile, but some of them became much, much larger, the size even of a T-Rex.
The footprints are from a huge crocodile-like creature called Postosuchus. It first appeared on the Earth around 230 million years ago. Then, some 30 million years later, its footprints suddenly vanished. But Postosuchus wasn't alone. Half of all land animals perished at the same time. The fossil evidence proves it to be one of the biggest mass extinctions ever recorded.
The evidence for this mass extinction is that we have lots and lots of fossils right in this area. And what you see is, especially in the reptile footprints, you see one group of forms, the forms that are related to crocodilians, disappear.
Whatever caused the mass extinction must have been a catastrophic event. Olson had a hunch that the mass extinction was somehow related to New York's return to the coast. The ancient area of New York sat on a line of great weakness, the plate boundary where two continents joined to form the supercontinent Pangaea. And it was unstable, prone to earthquakes and volcanoes. Olson's quest to find the evidence for the natural disaster that finished off Postasuchus 200 million years ago. A band of dark rock above the footprints in the New Jersey quarry caught his eye. It was basalt, the smoking gun Olson was looking for. Basalt is a volcanic rock. It forms when hot lava erupts onto the surface and cools. Did the volcanoes that forged this basalt trigger the mass extinction and also rip Pangaea apart? On its own, the evidence at the quarry was unconvincing. The layer of basalt is only a few feet thick. To prove mass lava flows caused this global catastrophe, scientists needed corroborative evidence. High above the Hudson River, geologist Matt Goring follows another lead. He's studying the Palisades, a dramatic geologic feature that hugs the Hudson River, beginning across mid-Manhattan and running into northeast New Jersey. They too are made of basaltic rock, the same rock implicated in the mass extinction of land animals. But the Palisades are on an altogether different scale.
The Palisades are a sheet of basaltic magma about 1,000 feet thick. It's about 40 miles long, so it's a very prominent set of cliffs that run all the way up the west side of the Hudson River.
Here is proof of massive volcanic activity. Hot lava flooded out of ruptures in the Earth's crust and covered ancient North America in a mile-deep sheet. The lava cracked as it cooled. The vertical ruptures formed regular pencil-shaped columns. These distinctive rock formations have been known to geologists since the 19th century. Intriguingly, they appear on both sides of the Atlantic, in North and South America, Europe and Africa. Geologists suspected that their presence pointed to the spot where Africa and Europe separated from America. But that was just an unproven theory. Until the 1950s, when scientists developed a revolutionary technique called paleomagnetism. Now, they could study the magnetic properties of rocks. Many rocks, including basalt, have a distinctive magnetic signature, formed as the rock is born. Tiny crystals inside the rock act like compass needles. When the magma that forms the rock is fluid, the crystals align to the Earth's magnetic field, pointing north. As the rock solidifies, the crystals freeze, forever locked in that fixed magnetic alignment. As continents move and the rocks travel, the crystals end up pointing in a different direction than north. Goring and his team investigate the magnetic signature of the Palisades. To get a sample, they bore into the rock with a water-cooled drill. They measure the exact orientation of the crystals today with a compass. When they offset this reading with magnetic north, they can calculate the original location of the rock.
14. One of the useful things that you can do with this rock is you can take it back in the lab and measure its magnetic orientation. And that magnetic orientation will be when this rock crystallized or solidified 200 million years ago. So this rock would have minerals that would be pointing in some other direction other than north today.
When scientists compared the magnetic orientation of the Palisades with the other basalt outcrops around the Atlantic, they discovered they formed at approximately the same latitude. Not only did the rocks have the same age, they were also born at the same location. For example, 200 million years ago, New York and Morocco were neighbors. The geologists had all the proof they needed. They could now confidently piece together what happened. It began with a global volcanic disaster.
About 200 million years ago, North America and Africa began to pull apart from each other. There were gigantic lava outpourings. These lava flows erupted along very long cracks in the Earth's crust that would produce fountains of lava extending thousands and thousands of feet into the atmosphere. They covered an almost inconceivably large area, roughly 4 million square miles, from southwestern France to southwestern Brazil, from New York to central Mali in Africa. This area was covered in ponded lava flows that in some places ended up being nearly a mile thick.
Volcanic eruptions led to soaring temperatures. Half of the plants and animals died. Postosuchus didn't stand a chance. As enormous forces tore Pangaea apart, a giant sea formed between the separating land masses, the Atlantic Ocean. The city of New York was now at the coast. $200-million-year-old footprints beneath a layer of basalt and the Palisades towering above the Hudson provide evidence that Pangaea split apart to create the east coast of North America. But the story of New York City was far from over. After being built by fire, the region was about to be overcome by another destructive force. Scientists are piecing together the story of New York's violent geological past. 250 million years ago, the Atlantic Ocean opened up, leaving the area of New York on the coast. But the maritime city still had a long way to go. There was no deep Hudson River channel. It was nothing but a small stream. What forces transformed it into the wide river capable of carrying heavy freighters far inland? A clue to how the Hudson Valley was created is the strange boulders that are scattered throughout Manhattan's Central Park. Some of them weigh several tons. But they're strangers to these parts, totally unlike the surrounding rocks. Geologist Charles Megarian investigates where they came from.
This boulder is a boulder from the Palisade Sheet on the other side of the Hudson in New Jersey. You can see it's very nicely polished. Compositionally, it's totally different than the surrounding bedrock, which is Manhattan schist. And the Manhattan schist here is very rich in mica. This rock has no light-colored mica in it whatsoever. The Palisade Sheet is located to the west and north of it.
The Palisades run for 40 miles along the Hudson River. Something immensely powerful must have moved the boulders such a great distance. Megarian knows the answer is ice. Scientists have noticed a similar phenomenon 4,000 miles away in the Swiss Alps. As huge glaciers grind their way across the landscape, they gouge out lumps of rock and carry them along in the base of the ice. These rocks act like sandpaper and carve out deep scratches. When the ice melts, it leaves the boulders behind. Megarian is convinced the same thing happened in Central Park. Ice moved the Palisade boulders and carved out grooves in the bedrock underneath.
This bedrock exposure in Central Park shows the profound effects of glaciation in the form of these spectacular glacial grooves that move up the outcrop and show this pattern where glaciers grabbed huge boulders, and those huge boulders acted like tools to produce these scratches.
To Megarian, the rocks in Central Park are compelling evidence that New York once was covered in ice. Over millions of years, growing and receding ice has repeatedly turned North America into a frozen wilderness. But the grooves on the rocks in New York don't tell the full story. The destruction caused by the ice points to a gigantic glacial event that would dwarf the future metropolis. To find out the extent of the ice, Megarian traveled to Bear Mountain, some 50 miles north of New York City. Once again, the clue was in the rocks. He found glacial marks similar to those in Central Park.
What we're looking at here are chatter marks. Chatter marks are very diagnostic features of glacial erosion. They're produced by boulders embedded in the base of a thick sheet of glacial ice. Those boulders impinged on this bedrock surface, polishing it, smoothing it off, and then plucking pieces of rock off as the glacial ice moved over with the boulders embedded in the base.
The gouges in the rocks could mean just one thing. The glacier must have been thousands of feet thick.
In this case, although we're standing at an elevation of about 1,280 feet above sea level, the glacial ice sheet covered Bear Mountain as if it weren't even there.
Scientists have found identical chatter marks on nearby peaks up to a mile above sea level. It was unmistakable proof. A glacier at least 1 mile thick ground its way across these mountains. Did this same ice sheet also plow through Central Park? Another nearby rock face provided the answer.
The feature that we're looking at here are a series of subparallel glacial scratches and grooves. These are produced by the glacial ice sheet dragging boulders across this very durable granite surface. It's kind of polished the surface, and in addition, it's produced these rather subtle, but obvious when the lighting is right, striae or grooves in the bedrock. Now, if we measure the orientation of these, these come out about north 20 degrees west, just about identical in orientation to the striae that we measured at Central Park.
It's significant evidence that the ice sheet that covered Bear Mountain also flowed over the surface of Central Park. Proof that New York City was covered by a glacier 4 times higher than the Empire State Building.
Just imagine glacial ice, a huge, thick ice sheet over a mile thick, exerting tremendous pressure on the surface and sculpting the surface into the landscape that we see today.
The ice sheet's crushing weight bulldozed everything in its path and cut through the remains of the ancient mountains. Before the ice arrived, the waters of the Hudson River had gently cut down through the landscape to form a V-shaped valley. But a mile-thick glacier takes no prisoners. It gouged out the sides and the bottom of the river valley and turned it into a U-shaped riverbed. The Hudson River was now navigable for big ships. The picture of modern-day New York was almost complete. Long grooves in the rocks in Central Park showed scientists that a vast ice sheet flowed over the eroded remains of these mountains. And marks and glacial striations on Bear Mountain proved this ice sheet was at least 4 times higher than the Empire State Building. When the ice melted, it left a vast ridge of debris blocking the Hudson River from the Atlantic. final challenge for geologists was to find out how the ridge was destroyed and how New York's harbor opened to the oceans. New York today boasts one of the largest natural harbors in the world. But it wasn't always that way. Towards the end of the last ice age, the port's wide entrance was blocked. 16,000 years ago, the melting glaciers left behind a 220-foot-high wall of debris. The ridge stretched from Long Island to Staten Island and forced the Hudson River through a narrow, more westerly course to the ocean. What powerful forces destroyed this rock jam? The prime suspect was a flash flood. But scientists needed evidence to prove that such a flood had happened. In the 1960s, fishermen made an unexpected find at the mouth of the Hudson River. They dredged up a giant mammoth tusk from the depths of the sea floor. Herds of these giant beasts roamed the plains of North America before they became extinct at the end of the last ice age. Finding the odd mammoth tusk here and there is not so surprising. But since the initial discovery, scientists have found hundreds more tusks and bones in the mouth of the Hudson River. It was as though a violent torrent swept the mammoths away and dumped their remains off the coast. And there were more clues nearby. Huge boulders resting on the sandy sea floor. Some of them as big as cars. The boulders must have been part of the ancient moraine that once ran between Long Island and Staten Island. Geologist David Franzi knows that only a raging torrent could have shifted them.
Based on the size of the boulders that we see here, we know that that flood must have discharge on the order of 1.5 million cubic feet per second. That's 3 times larger than the largest Mississippi River flood ever recorded.
And all that water had to come from somewhere. Scientists began looking for the source of this flood. A flood powerful enough to transport huge boulders all the way to the sea.
Rocks to a geologist are like pages in a history book. For us, erosion oftentimes rips some of the pages out of our history book, so it's the job of the geologist to put together a fragmentary record into a coherent history of events that happened in the past.
300 miles north of the city, in upstate New York, Franzi tracked what might have been the flood's path to an unusual grove of trees on Covey Hill in the Adirondack Mountains. The trees are jack pines. They are rare in this area, where the soil is usually fertile and deep. But on Covey Hill, their presence shows that there is no more than a few inches of soil on top of the bedrock.
The jack pine is essentially rooted right on the top of the rock surface here. This is a bare sandstone surface, very little mineral soil, and it's subject to prolonged periods of dryness during the summertime. Jack pine's adaptations make it able to survive here where no other tree species can.
What happened to the soil? The jack pines continue to grow at the entrance of a long gorge over 300 feet wide. Usually, gorges like this are cut down over thousands of years, but in this case, the missing topsoil points to a sudden flood event. A raging torrent must have ripped away the soil and cut deep into the rock. In a helicopter, Franzi follows the gorge west. Eventually, it opens into a vast, empty basin, located next to one of the Great Lakes, Lake Ontario.
It doesn't take much of a stretch of the imagination to imagine this valley filled with water and then with these hills poking up through his islands.
16,000 years ago, this basin was filled with 2 billion cubic miles of water. A huge lake geologists call Lake Iroquois. It formed at the end of the last ice age. As glaciers receded, the meltwaters slowly filled up the lake. The ice dams holding the waters weakened. Eventually, the dams collapsed, causing sudden and devastating flash floods.
Lake level dropped on the order of 70 feet, and about 160 cubic miles of water were released into the Champlain Valley catastrophically. That flood water would have coursed down the Champlain Valley, through the Hudson Valley, and ultimately out into the Atlantic Ocean.
The torrent raced towards New York City, 300 miles to the south, then took the straightest course to the sea. The floodwaters smashed into the ancient moraine, the huge pile of debris blocking the direct exit of the Hudson River.
The bridge we see behind me spans the channel that was cut by the flood event. When the flood wave came through, it was of sufficient intensity to overtop the dam and very rapidly cut the channel.
The gap that was created by the flood still exists. It's now a tidal strait called the Narrows. Today, the gap is spanned by the Verrazano Bridge. The channel is deep enough for even the biggest ocean-going ships. It's the most important entrance to New York City's harbor. Mammoth tusks and huge boulders at the mouth of the river showed scientists that there was a torrent big enough to blast a hole through the ancient moraine. And a channel leading towards the Great Lakes revealed the source of the flood. It was this flood that created the Narrows and gave New York a wide entrance to its port. A unique geology laid down the foundations for New York City. But the same forces that constructed it may also have sown the seeds for New York's destruction. Scientists have pieced together the half-billion-year history of New York City. Huge mountains, volcanic eruptions, and glacial ice shape the area. But New York's story doesn't end here. The geology that created one of the greatest cities on Earth also has the potential to destroy it. Experts have been studying the potential threat to the city.
We're standing here in Lower Manhattan on one of our major thoroughfares, Canal Street. And it's important because in 1821, a Category 2 hurricane raised the water level at the Battery 13 feet in 1 hour. And literally, the Hudson River met the East River, and Canal Street was covered by water, and Manhattan was actually 2 islands for 3 hours until the water receded.
New York City is vulnerable because of its position on the coast. Long Island stretches northeast at a right angle from the New Jersey shore. New York City is nestled behind the western end of Long Island. Normally, the island protects the city from the sea. But when hurricanes threaten, the opposite is true. Long Island becomes a dangerous liability. Hurricanes racing north along the beaches of the Atlantic coast pile up huge bulges of water in front of them. They're called storm surges. Hitting the right-angle junction at Long Island, the winds funnel the storm surge in through the Narrows, the gap between Long Island and New Jersey.
This is the place at the actual apex of the right angle in New York where all the water being pushed by a hurricane would be concentrated. And in the distance is the Verrazano Bridge, and all that water is going to go through the passage we call the Narrows, and it's going to be accelerated toward New York City, where it will rise to abnormal heights.
Experts believe that in the United States, New York is the third most vulnerable city after Miami and New Orleans to a hurricane disaster. If it was hit today, the consequences would be serious.
New York City is hit by hurricanes only infrequently, like in 1821 and in 1893 and in 1938. However, the point is that the hurricane that will eventually hit New York City again will be catastrophic. And what is going to happen when the utilities are knocked out? What is going to happen when salt water reaches into the subways and ruins the electrical system? We're talking about unbelievable amounts of money to restore the infrastructure. We're talking about setbacks and delays in commerce and banking and transportation. A catastrophe that's never been seen.
Storm surges are not the only threat to New York's future. Earthquakes are also part of the vast geological forces that shape this area. They are still at work today. Some could change the city in an instant. November 4th, 1884. New York City was shaken by an earthquake that lasted 10 seconds. The Brooklyn Bridge swayed and people panicked. The earthquake showed 5.5 on the Richter scale. January 17th, 2001. New York City was struck again. This time, the quake was relatively small, only 2.4, but it struck right under 125th Street.
The earthquake in 2001 is the first earthquake that we could confidently locate in Manhattan. That's its claim to fame. It was felt widely.
It's impossible to study the cause of the quakes at the surface. The evidence is buried beneath the city. Deep within New York's bedrock, seismologist Leonardo Sieber studies the cause of these quakes. In a subway tunnel 100 feet beneath the bedrock under the East River, there is a ready-made laboratory. Here, Sieber can study the rocks up close and personal. It is the same bedrock Manhattan is built on. But Sieber fears it isn't as solid as once was thought.
New York area is considered a seismic zone, meaning there's a cluster of known earthquakes that have occurred in this area. So we are, as geologists, very eager to discover which faults are responsible for these earthquakes.
The majority of earthquakes occur at the boundaries between separate sections of the Earth's crust, the tectonic plates on which the continents sit. But New York's earthquakes are different. The city is firmly in the middle of a tectonic plate, halfway between the Mid-Atlantic Ridge to the east and the San Andreas Fault to the west. Sieber is anxious to discover what's going on. As he examines the walls of the tunnel, he comes across a possible clue. The long fractures in the rock are fault lines that formed when pressure built up. As the tension was released, the rock cracked and shifted. This is felt on the surface as an earthquake.
This is an example of a very small fault, but is a fault that probably did generate some small earthquakes. When one of these faults generated an earthquake, we think that perhaps other faults of the same family can generate earthquakes.
These faults in New York's bedrock are evidence that the area was hit by earthquakes in the past. But Sieber has no way of knowing if the faults are still active and dangerous. If a large earthquake hit New York today, the consequences would be catastrophic.
A large proportion of New York City buildings are simply not built to withstand earthquake shaking. We worry about transportation tunnels, in particular tunnels that traverse rivers, where parts of the tunnels are rooted in solid rock and other parts are resting on soft sediment. The oscillation of these two different materials could cause severe cracking and fracturing. The infrastructure would be severely damaged. It would take tens of years to repair the damage caused by such a large event.
With the evidence geologists have collected, the story of the creation of New York City can now be told. The city's bedrock was formed under a chain of mountains over a mile high. Volcanoes and lava fields over millions of square miles split up the ancient supercontinent and created the east coast of North America. Glacial ice, 4 times as high as the Empire State Building, carved out the deep Hudson River. A catastrophic flash flood broke through the moraine to form the Narrows and opened up New York City's harbor to the oceans. Looking ahead to the distant future, geologists see more challenging times for the city. In 40,000 years, they predict this region will be engulfed by another ice sheet. And in 250 million years, the Atlantic will start to shrink again. Europe and Africa will eventually crash back into the American coast. The fossilized remains of the once great city of New York will become just another layer of rock in a vast new mountain range. A footnote in the immense, ever-changing story of planet Earth. Earth, a 4.5 billion year old planet, still evolving. As continents shift and clash, volcanoes erupt, glaciers grow and recede. The Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, Loch Ness in the Highlands of Scotland is explored. It holds more water than any other lake in Britain, with a bedrock containing some of the oldest rocks on the planet. Set in a landscape that was once part of America, Loch Ness is a lake with an enduring myth, the Loch Ness Monster. A team of scientists investigate how Loch Ness was made. The clues they uncover also provide a window into the formation of the Earth itself. Deep, dark, and full of mystery. This is Loch Ness in the Highlands of Scotland. For 1,000 years, there have been claims that this vast lake hides a strange and terrible secret, the fabled Loch Ness Monster. A mythical beast, suggested by some as a descendant of the dinosaurs which once roamed this part of Scotland. Loch Ness would be the perfect hiding place for a prehistoric monster. At 23 miles long and a mile wide, this vast freshwater lake covers the same area as New York's Manhattan Island, and it's more than 700 feet deep. But the monster is not the only mystery that surrounds Loch Ness. In the hills above the loch, there is a type of rock whose origin baffled scientists for years. It's a sandstone, and it's the start of the investigation into how Loch Ness was made.
It's known as the Old Red Sandstone, and it's given that name because it's red and it's a sandstone. And it's called old because it's about 350 million years old.
The Old Red Sandstone runs down one side of Loch Ness. But the most astonishing fact about these rocks is not their age, but where they come from.
These rocks actually belong to my homeland of North America because these rocks originated on the North American continent and then have separated from North America. But in many ways, this is almost a little bit of home for me here in Scotland.
But how do geologists know that this Old Red Sandstone comes from 3,000 miles away, on the other side of the Atlantic Ocean?
These rocks are identical in age and character to the rocks that actually form the Catskill Mountains. And so this part of Scotland belonged to northeastern North America.
For more than 1,000 years, old red sandstone has been used for building castles in this part of Scotland. But it's also been quarried in the US and used for brownstone buildings in New York City. Under the microscope, rocks from both continents have an identical crystal structure, and chemical analysis has also proved that they're exactly the same age. But how did part of America end up on the shores of Loch Ness? To answer this crucial question, the investigation must go much further back in time to look for evidence in the ancient bedrock of northern Scotland. It's here that the story of Loch Ness begins. The trail starts north of Loch Ness, where the bedrock comes to the surface. This landscape is full of the extraordinary mysteries of an unimaginably ancient past. It's made of a type of rock called Lewisian gneiss. Recent drilling and blasting for a new road cut have exposed evidence which uncovers an amazing chapter in Earth's history. The long straight lines are the drill holes left in the rock face. Modern radioisotope dating has given geologists the first clue to understanding the origin and formation of these rocks.
These rocks are very special to geologists. They're some of the very oldest rocks in the world. We see them in very few places, perhaps a dozen places across the globe contain rocks of this age. Talking about 2.5 to 3 billion years old.
The origin of the gray Lewisian gneiss lies in the first crust that cooled on the surface of the Earth. After its formation 4.5 billion years ago, parts of this crust were mixed together with the earliest sediments, buried, remelted, and forced back up again and again for more than 1 billion years. These extraordinary rocks are the result of that devastating period in our planet's history. And there's more evidence exposed in this road cut, revealing crucial information about the early history of the Loch Ness region.
This exposure contains 3 important pieces of geological jigsaw puzzle. First, we have the grey gneiss, 2.5 to 3 billion years old. Secondly, we have this black igneous material which has been intruded into the area. This is 2 billion years old. And thirdly, we have this pink granitic intrusion that both intrudes the black material and the gneiss, and this is 1.8 billion years old.
This evidence reveals that after the formation of the Lewisian gneiss, much younger rocks were then melted and mixed into the ancient crust. But this process took an incredible length of time.
What we've got here are rocks that record over 1 billion years of Earth history. Now, to put that into perspective, that is almost 1/4 of the age of the Earth recorded in this exposure.
This is the bedrock of Loch Ness. It carries an extraordinary story of a major part of Earth's history. And there are yet more secrets hidden in these rocks.
It looks very much because of the temperatures and pressures that these rocks were under, that they've been to depths of perhaps 50 miles beneath the Earth's surface in the past. This suggests that these rocks have been to hell and back 2 or 3 occasions over 1 billion year period.
Geologists now know that the only force powerful enough to produce this extraordinary mix of rocks is plate tectonics. Plate tectonics is the process by which the giant plates of the Earth's crust are driven slowly across the planet's surface by vast convection currents deep in the Earth's hot mantle. In the Loch Ness region, the evidence in the road cut reveals that incredible pressures forced the crust deep down into the Earth, where it was melted, deformed, mixed together, then finally brought back to the surface. After that, for another 1 billion years, this ancient landmass quietly eroded down to a rough, rolling landscape. But this wasn't the green terrain we see now. There was much less oxygen in the Earth's atmosphere than today, and the surface would have looked like a lunar landscape, desolate and sterile. Incredibly, remnants of that billion-year-old landscape are still preserved today. The clues are revealed in another road cut, where the trained eye can draw amazing conclusions from what looks like a jumble of rocks.
At this road cut, we can see Lewisian gneiss, which is between 2.5 and 3 billion years old. But up here, we have something completely different. If I go up to this level and look above it, we have horizontally bedded red sandstones.
This sudden change in rock type helps to unravel the mystery hidden in these ancient formations.
They're believed to have been laid down in a continental environment by rivers. We've got river systems that laid down horizontally bedded sedimentary rocks on an ancient landscape.
So this simple outcrop reveals that even in a world with little oxygen, the ancient bedrock of Scotland was covered in rivers 1 billion years ago. And there's yet another secret hidden here.
There is a junction between these rocks, which are almost 1 billion years old, and the rocks below are 2.5 to 3 billion years old. This is a major time gap of between 1.5 and 2 billion years.
The time gap revealed here is extraordinary. It shows that after the traumas of their early formation, the rocks of the Loch Ness region went through a period of calm, which lasted more than 1/3 of the age of the Earth. The investigation into how Loch Ness was made has uncovered its first evidence. Identical old red sandstone found on 2 continents proves that Scotland and America were once joined together. Some of the oldest rocks in the world reveal that the bedrock underlying Loch Ness was made during the primeval creation of the Earth's crust. Bedded sandstones lying on the ancient bedrock show that rivers flowed over this landscape 1 billion years ago during a long period of tranquility. But the calm couldn't last forever. A major continental collision was looming, and with it the union between Scotland and England. The investigation into how Loch Ness was made will next uncover the geological structures which would eventually create Loch Ness. The search for evidence begins with a 19th century scientific mystery. In the 1880s, geologists in Scotland were baffled by a sequence of rocks they found north of Loch Ness. Here in a remote hillside lay the problem. A huge mass of very old Lewisian gneiss was lying on top of much younger rocks. But the 19th century geologists had never encountered this before. In their experience, younger rocks always lay on top of older beds. Then, one scientist invented a novel approach to try to solve the puzzle.
A survey geologist back in the Victorian age, 125 years ago, mapped this area, and his name was Henry Cadell. He went back to Edinburgh and he worried about what he'd seen in the field and thought, how do I replicate what I've seen? How does this happen? So he built a model and he attempted then to show, using the model, what it was that he saw in the field.
Cadell's model was simple. He suspected that some force had squeezed the rocks horizontally to make this upside-down sequence, so he built an apparatus containing layers of sand and clay to test his ideas. Professor Underhill is using a replica of Cadell's equipment, filled with alternating layers of black sand and plaster of Paris, to try and duplicate Cadell's experiment. Turning the screw winds the block forward, imitating the horizontal pushing force that Cadell thought was the culprit. As the horizontal force increases, the layers are pushed over each other along a shallow plane, which geologists now call a thrust fault.
And we've got the first thrust appearing.
Oh, look at that. Another thrust going in.
The experiment showed cattle exactly how older layers, the ones on the bottom, are pushed over and on top of the younger layers along the plane of the thrust fault.
There's some beautiful structures in here. There's a thrust fault running through here, which duplicates the white layer. And another one through here, and the final thrust fault, which is at the lowest angle, out here towards the left-hand side. A success in terms of a simple model replicating what we see on the ground. And I can see how Cadell and others, when attempting such things, began to understand what it was that they saw in the field. They could replicate it in a simple, crude model, but replicate it in a very successful manner.
Once Cadell and his colleagues understood the principle of thrust faults, the apparently illogical sequence of the rocks they saw in northwest Scotland began to make sense.
Well, the slope represents a thrust fault. What we have underneath it is a bedded, younger quartzite succession, which is pink. Above it, the grey rock, the rubbly grey hillside we see above, is the Lewisian gneiss again. And the surface in between, which is putting older rock, the grey material, onto the pink rock, the younger material, is the thrust fault, just like in the model that we saw before.
Geologists now know that a thrust fault is the smoking gun that shows where continents have collided. But which continents were colliding to make the thrust faults in Scotland? And how were they involved in making Loch Ness? The scientists' trail now led them to another thrust fault, the Moyne Thrust. The Moyne Thrust is one of the biggest thrust faults on Earth. Running for 120 miles down the northwest of Scotland, it's mostly hidden from view. But Professor Underhill has found one of the rare locations where the thrust can be seen on the surface. This apparently insignificant join between two rock layers is the actual line of the thrust. And it reveals a geological bombshell. The dark layer above the thrust comes from England, but the surprise lies in the yellow limestone below it. Just like the old red sandstone at Loch Ness, this rock comes from North America. This one small piece of evidence has enormous implications for the formation of Loch Ness.
The amazing thing about this contact is that it's the meeting point between two continents. So here we are on a wet Scottish hillside on a Sunday afternoon, and I am touching the contact between effectively America and northwestern Scotland on one hand and England on the other, as was 425 million years ago.
But how did these two ancient continents collide? 450 million years ago, a supercontinent containing North America and Scotland lay deep in the southern hemisphere. At its margin was an ocean wider than the present-day Atlantic. On the other side was England and Europe. But the forces of plate tectonics were slowly pushing the two land masses together.
Well, around 450 million years ago, there was a major ocean where we're standing now. It was called the Iapetus Ocean, and it separated America and northwestern Scotland on one hand from effectively southeastern Scotland and England on the other hand. Now, what happened in the 20 million years after that, that ocean closed, and eventually was closed sufficiently that two continents collided into each other.
The collision between America and Europe pushed massive layers of rock over each other, forcing upwards a range of mountains higher than the Himalayas are today. Still firmly attached to America, Scotland and England became fused together. But what did this collision have to do with the making of Loch Ness? The loch itself provides the most fundamental evidence.
One thing that's quite striking about Loch Ness is that when you look at it, particularly from this perspective, you can see that it runs straight, almost straight as an arrow. And that straightness goes on for about 20 miles. And as a geologist, that tells me that there has to be a control on this topographic straightness because nature doesn't produce things in straight lines. And so there is a structure here that is controlling the overall shape of Loch Ness itself.
This structure is the Great Glen Fault,
a major geological fault line formed during the continental collision 425 million years ago. It runs for more than 300 miles right across Scotland, slicing the country in two. Loch Ness exactly follows the line of the Great Glen Fault.
The Great Glen Fault is not a thrust fault like the Moyne Thrust, where material has been pushed up over. It's not a normal fault where material drops down vertically. It's lateral motion. The Great Glen Fault is Scotland's version of the San Andreas Fault. It's just 400 million years older.
The Great Glen Fault is no longer active, but this giant split in the Earth's crust has been a feature of the Scottish landscape for more than 400 million years. It's the foundation of Loch Ness, and without it, the loch could not exist, nor could the legend of the Loch Ness Monster. The investigation into how Loch Ness was made has uncovered more evidence. The discovery of thrust faults showed geologists what happens when continents collide. Yellow limestone from North America found at the Moyne Thrust proves that America and Scotland crashed into England 450 million years ago. And the shape of Loch Ness reveals the straight line of the underlying Great Glen Fault, formed during that continental collision. After the collision, the forces of plate tectonics drove Scotland south, round the surface of the Earth. Now, the investigation must follow its amazing journey. The next step in the investigation into how Loch Ness was made traces Scotland's journey round the surface of the Earth, driven by the forces of plate tectonics. Understanding what the environment was like in the past gives clues to the location of Loch Ness millions of years ago. So the investigation now moves on to the Jurassic period, 165 million years ago. The trail leads to the Isle of Skye, an island off the west coast of Scotland. At Staffin Bay, there is an incredible piece of evidence which sheds light on this period in Scotland's past. Astonishingly, it lay in plain sight but undiscovered until 1994, when an amateur geologist made an extraordinary find. On the flat, rocky shoreline of this popular beach, he discovered a fossilized footprint of a giant dinosaur. Dr. Anjana Katwa has come to analyze the details of this remarkable evidence.
When you walk across these ledges, it's just an incredible feeling to think that dinosaurs walked on the same ledge that I'm walking on now, 165 million years ago. This ledge, we've got this wonderful Megalosaurus footprint. The Megalosaur was a 25-foot high carnivorous dinosaur, quite a formidable predator during Jurassic times.
With some individuals standing as tall as a football goalpost, Megalosaurus was a fearsome monster. But how could something as temporary as a footprint be preserved for 165 million years?
The footprints are so unique. What's happened is that a dinosaur has travelled over a kind of sticky, gooey mud, and their impressions have been left behind. That mud has dried off and it's hardened, and then over time, wind-blown sand has come in and covered that footprint over. And then as further time has developed, we get layers of clay and sand building up over that footprint, and that footprint becomes fossilised over time. Now, over a few million years, erosion occurs, and those footprints become exposed for us to see today.
Dr. Katwa is making a plaster cast of one of the footprints, so she will be able to examine it more closely.
We take the casts in order to have a record of the footprints, so we can take them back to the lab and have a look at them and understand how this creature used to live.
As she carefully removes the plaster cast, its shape reveals a 165 million year old secret.
One thing that really strikes me actually is the deep impression that this front toe is made and how pointed it is. And this tells me that this dinosaur was moving at a fast speed and really pushing down on its front three toes. So it might have been chasing some kind of prey.
But Megalosaurus wasn't the only dinosaur to leave its footprints in these rocks only 60 miles from Loch Ness.
This is the smallest dinosaur footprint that anybody has ever found in the world. You can actually see it's about the size of my fingernail. And we think it's a coelophysis, and it's quite interesting because the small footprint here, which we think is from a hatchling, is embedded in the larger one here that you can see. What we think this tells us is that the young travelled with their parents in groups, and that most probably the adults were looking after the young.
Geologists have used the amazing evidence of the footprints of Coelophysis and Megalosaurus together with the muddy rocks they were found in to better reveal the story of Loch Ness in the Jurassic period. At the time, Scotland was still attached to America. Plate tectonics had driven this landmass much nearer the equator, 2,000 miles further south than it is now. And that had a major effect on the climate and environment of Loch Ness.
Back during the Jurassic times, the climate and the environment was very, very different to what we see today. There would have been lush jungles full of tropical vegetation, and the dinosaurs would have been living on the edge of these jungles, travelling over lagoonal type of wetlands. This climate was ideal for dinosaurs to live in because it supported a huge ecosystem of wildlife that they would have predated on.
The bones of one more dinosaur have recently been found on the Isle of Skye, the plesiosaur. But this discovery generated a completely different kind of interest. Enthusiasts see a strong resemblance between the shape of the plesiosaur and some descriptions of the Loch Ness monster. Could a descendant of the long-extinct plesiosaur really be the source of the legend? The evidence to unravel the extraordinary geological history of Loch Ness is getting stronger. The findings of Megalosaurus and Coelophysis footprints prove that dinosaurs lived in Scotland 165 million years ago, and that Loch Ness was then a subtropical paradise 2,000 miles further south than it is today. But about 60 million years ago, 5 million years after the dinosaurs became extinct, plate tectonics would tear Loch Ness and America apart. The investigation into how Loch Ness was made now moves forward to a time 60 million years ago. Scotland and America are still firmly joined together. The next question is, when and how did they become separated? On the Isle of Skye, the landscape is full of evidence which can unlock the secrets of this turbulent period in Scotland's past. At Talisker Bay, the massive sea cliffs provide the first clue to the events that devastated the region. They're made entirely of volcanic lava.
I'm standing here on a single lava flow, and this lava flow is only about 10 feet thick. But this whole cliff above me is made up of lava flows, maybe 150 feet or more, and stretching for miles in all directions. Now these lava flows are composed of basalt, the same type of rock that is being erupted today from modern volcanoes like Hawaii or Iceland.
Geologists have calculated that these basalt lavas on Skye are about 60 million years old. But where is the volcano which erupted them? The clue comes from a range of mountains on the southern tip of Skye, the Cuillin Hills. It's the type of rock that makes up these craggy peaks which provide the evidence.
They're made of a rock called gabbro. Now these are the same chemical composition as the basalt that's been erupted onto the surface, but there's a difference. The basalt that was erupted was cooled very quickly because it was exposed to the air. Geologists call that fine-grained. On the other hand, the magma that was trapped maybe a mile down beneath the Earth's surface, that cooled pretty slowly. It was kept warm for quite a long time. And so you've got very large crystals growing. And when you get a rock with large crystals, that's what we call coarse-grained.
The large crystals in the Gabbro rocks give away their origin. They tell geologists that the Kulin Hills are the remains of an enormous magma chamber deep below the volcano, where lava was stored before being erupted onto the surface. But how much lava was there?
We may be looking now at a beautiful green valley, but actually all these hills around here are made up of rocks that were formed in a series of massive volcanic eruptions about 60 million years ago. And at that time, there were volcanoes erupting all over Scotland. Here we are on Skye, and this is just one of those volcanoes.
It's now known that an incredible 500 cubic miles of lava was erupted on Skye alone. That's enough to cover the whole of Texas with a layer of lava 10 feet thick. But this was just the tip of the iceberg. The rocks themselves reveal that volcanoes erupted all over Scotland on a massive scale. The evidence is here. Huge regular columns in the lava flows, looking like they've been carved out of the rock. In reality, these amazing formations are made by gentle cooling of thick lavas. Exactly the same type of columns are found in outcrops of basalt lava 80 miles away off the west coast of Scotland. And as far away as the coast of Ireland, 150 miles from Skye. These lavas have all been dated at about 60 million years old, and they were also part of the same series of massive eruptions which spread out for hundreds of miles in all directions. But what was the cause of the eruptions? Dr. Goodenough has found another clue which points to the origins of these lavas and their role in the creation of Loch Ness.
This is the ropey top to a lava flow. In Hawaii, they call it pahoehoe. And what happens is that the lava gets a thin skin on its surface as it cools, but it's still flowing underneath that skin. And the thin skin wrinkles and gets pushed forward, giving this ropey texture that we can see here. But it's really quite rare to see them like this in these old lava flows. But it tells us a lot about the type of magma that was erupting from that volcano.
Geologists know that this kind of magma comes from deep within the Earth. It usually erupts on the surface when tectonic forces split the Earth's crust apart. Is that what happened here 60 million years ago?
At that time, Scotland was still joined to North America, but the two continents were being stretched and thinned due to tectonic forces. And that allowed molten rock, or magma, from deep within the Earth to well up and to be erupted from those volcanoes. And eventually, that volcanic activity led to the development of a new ocean between Scotland and North America, the Atlantic Ocean.
So the lavas are the trail of evidence which show that the opening up of the Atlantic Ocean began with volcanic eruptions all over Scotland. As magma erupted under the ocean, the seafloor spread out, slowly pushing Scotland and America apart. The birth of the Atlantic Ocean had a direct effect on the making of Loch Ness. As the ocean grew, the huge forces involved reawakened the 400 million year old Great Glen Fault.
So faults like the Great Glen, these are zones of weakness in Earth's crust. And they're like scars or wounds. They can reopen. And in the case of the Great Glen, it was reactivated when the Atlantic began opening 50 to 60 million years ago. And this is why you see this feature now present in today's landscape, even though the fault itself is 400 million years old.
The massive geological movements shattered and weakened the rocks along the fault. Along this line of weakness, a river started cutting down through the shattered rocks, slowly carving out a valley. For the next 55 million years, the landscape of Scotland weathered and eroded. The outlines of the mountains softened, and the coastline began to take on its present shape. Loch Ness became a long river valley, following the line of the Great Glen Fault. The investigation is close to uncovering the final stages in the story of how Loch Ness was made. Huge huge lava flows on the Isle of Skye reveal that massive volcanic eruptions 60 million years ago were the start of the separation of Scotland and America. The sharp outline of the 400 million year old Great Glen Fault shows that the fault was reawakened as Scotland and America were torn apart. But there was one final land-changing event to come. Nature wasn't finished with Loch Ness, and it was this event that created the lake we see today. Tracing a violent history that lasted for 3 billion years, the investigation into how Loch Ness was made now moves forward to the recent past, only 10,000 years ago. The final link in the chain of evidence is to discover how the wide, deep waters of Loch Ness were finally made, and whether a descendant of the dinosaurs could possibly have survived there to create the myth of the Loch Ness Monster. A vital clue was uncovered in the 19th century by one of the greatest scientific minds the world has ever known, Charles Darwin. In 1838, Darwin came to Scotland to investigate a mystery in the remote valley of Glen Roy, about 20 miles from Loch Ness. For hundreds of years, people had been baffled by 3 extraordinary parallel lines which run round both sides of the valley. Strange horizontal cuts in the hillside, in some places more than 30 feet wide. These parallel roads, as they are called, run exactly level for more than 20 miles. What could have made them? Dr. Pete Nino is following in Darwin's footsteps to the Glen Roy parallel roads and the story they reveal.
Their creation was a mystery for a very long time, and initially people just thought they were perhaps created by giants, a thing of myth or legend. And then in the 19th century, a number of scientists came here, including Charles Darwin. And when he saw them, he thought they were exactly the same as features he'd seen in South America, where earthquakes had uplifted old marine shorelines and left them abandoned higher up from the sea.
Darwin was so convinced the parallel roads were the remains of old seashores that he published a paper with his results, and the world of science believed him. But for once, Darwin was wrong. In 1840, 2 years after Darwin's visit, a Swiss scientist named Louis Agassiz came to Glen Roy. Agassiz had spent a lifetime studying glaciers and the effects of glaciation on the landscape of the Swiss Alps. When he examined the parallel roads, Agassiz realized that they were ancient shorelines, but that the valley had been filled not by the sea, but by a freshwater lake. From his knowledge of glaciers in the Alps, Agassiz was able to show that a freshwater lake had once filled the valley. The lake was kept full by a huge glacier which blocked the end of the valley. As the glacier melted and froze again 3 times, the water in the valley emptied and filled up to a different level, carving out the 3 relic beaches.
Initially, Agassiz wasn't believed because people believed Darwin, and then over time it became clear that Agassiz was correct, and Darwin claimed it was one of his great embarrassments that he got something so terribly wrong, which sort of shows that even great scientists can make mistakes.
The evidence at Glen Roy convinced Agassiz that many features in the Scottish landscape must have been made by glaciers, and that led him to the startling conclusion at the time that the whole of Scotland had once been covered by ice.
And the moment you make that leap that what you've got here was created by glaciers, you've instantly got to make the leap to the fact that we must have had a very cold climate here in the past, cold enough for ice sheets and glaciers to build up. This site is of world importance in terms of the understanding of glaciations and the fact that in the past ice covered a much larger proportion of the planet than it currently covers.
This extraordinary investigation led eventually to the idea of the Ice Age, periods in the geological past when much of the northern hemisphere was covered in glaciers and ice sheets. Since Agassiz's discoveries, scientists have been investigating the role of ice in making Loch Ness.
About 2.5 million years ago, the global climate started to cool. And since then, we've had a series of repeated glaciations, roughly about once every 100,000 years.
Each time the ice advanced, temperatures plummeted. Average winter temperatures were at least 30 degrees colder than today. As the ice built up, it reached extraordinary thicknesses.
The ice sheet over the centre of Scotland would have been 3,000 or 4,000 feet thick. And here in Loch Ness, it would have certainly been a couple of thousand feet thick. You might have seen a few of the highest mountains just peeking out the top of the ice sheet, but in the main, the whole of the landscape would have just been blanketed by ice.
But what effect did this vast weight of ice have on the creation of Loch Ness? The loch itself is difficult to investigate because it's full of water. But there's another location where the evidence is clear. Just 20 miles from Loch Ness is the forbidding valley of Glencoe. Glencoe is a legendary place in Scottish history, as it was here that an infamous massacre took place in 1692, when the MacDonald clan were murdered in their beds by the Campbells. The shape of this valley sheds light on the way Loch Ness was made.
If you could actually drain the water out of Loch Ness, what you'd actually end up with is a valley with this sort of shape. And looking down Glencoe, you can see it's a very, very steep-sided, flat-bottom valley. And it's basically been created by glaciers repeatedly flowing down the valley, eroding it, and basically gouging out what was originally a V-shaped valley and turning it into an over-deepened U-shaped valley.
Glaciers are extremely efficient at eroding the landscape. They pick up vast amounts of rock debris, which is carried along at the base of the glacier. With the weight of millions of tons of ice on top of it, this rock debris grinds away the bedrock like sandpaper, scouring and deepening the valleys to a characteristic U-shape. Across Scotland, there are hundreds of valleys with this distinctive U-shape, bearing witness to the huge number of glaciers which once covered this whole region. At Loch Ness, underwater mapping has revealed that the loch has this signature U-shape. It's flat-bottomed with very steep sides. In some places, only 50 feet from the shoreline, the water is over 500 feet deep. Further proof that Loch Ness was made by a glacier. There was already a long river valley which had formed along the line of weakness created by the shattered rocks along the Great Glen Fault. Then, during the last ice age, a giant glacier flowed down the valley, slowly carving out Loch Ness.
As ice flows down it, it scours it out, deepens it, and over a series of glaciations, it deepens it to the extent that it's now, a loch 750 feet deep.
The investigation is now faced with two final questions. How did Loch Ness fill up with fresh water, and what keeps it full? Loose rock and boulders found on a huge ridge 250 feet high at the head of the loch could provide the answer.
The immediately obvious thing about these large rocks is that they're extremely smooth and well-rounded, and that indicates that they've been transported by water. They're also very large, this is very heavy, so you need a lot of energy, so that tells you that you've got a lot of meltwater that's carried it and then subsequently dumped it where we are now.
This evidence, combined with discoveries about climate change, shows what happened here. About 10,000 years ago, global temperatures rose rapidly, the ice began to melt, and the glaciers retreated.
Glaciers down there would have been eroding Loch Ness, bringing up large amounts of sediment, and that sediment is then being transported in this direction by the flowing ice and also by flowing meltwater.
As the ice melted, a huge river formed under the Loch Ness Glacier, carrying with it vast amounts of rock debris.
And then what we've got here, what we're standing on, is in effect the zone where the glacier is now dumping that sediment.
Millions of tons of rocks created an enormous plug which dammed the river and stopped the water from escaping. As the ice melted, the valley filled up, finally making the lake we know as Loch Ness. Loch Ness is only 10,000 years old, but the investigation into its history has revealed an amazing story. Old red sandstone rocks show that Scotland and the US were once joined together. The shape of Loch Ness is controlled by the Great Glen Fault, formed when Scotland and America crashed into England more than 400 million years ago. Fossilized dinosaur footprints place Loch Ness near the equator during the Jurassic period. Lava flows reveal that massive volcanic eruptions 60 million years ago began the separation of Scotland and America. And the profile of Loch Ness proves that it was carved out by glaciers 10,000 years ago, finally creating the Loch Ness we know today. But what of the Loch Ness Monster? The iconic image is now known to be a fake. But is there any way that the mythical beast could be a descendant of the dinosaurs?
We have two geological facts that tell us that Loch Ness cannot be inhabited by a dinosaur. One is the dinosaurs died a long time ago, and the loch itself, geologically, is very young. Dinosaurs went extinct 65 million years ago. So 65 million years to 10,000 years is a long time distance, and there is no chance at all that you would have preserved in this loch an ancient monster from times millions of years ago. The loch's too young.
So the geological evidence proves that Loch Ness could not be home to a dinosaur that somehow survived there since the Jurassic. The awesome geological history of Loch Ness has thrown up many mysteries. But for science, the Loch Ness Monster is not one of them.
Earlier today, TNA cameras, yes, they were on hand to document the arrival of the competitors in our world